that will be presented here in Spire. Author of accepted paper come from 14 countries across 4 continents. The proceedings are published at Lecture Notes in Computer Science by Springer in that volume. You can access the proceedings from our website. You cannot just take the URL and paste it. Just to have to access the website using program, then proceedings, and then click on that link over there, and you will get them. Okay. We have an amazing program in the next 4 days with 23 technical talks, 2 keynote speakers. We will have Lena talking us in brief, a tutorial every day. I mean, the first 3 days of the conference, a social event tomorrow, a best paper award ceremony on Thursday, I think, a business meeting, and a workshop on compression text and algorithm on Friday. So we hope you enjoy this program we have for you. And we also want to thank the program committee members and the external reviewers for helping us to do the hard work, the hard reviewing work. And also, of course, the organizing committee, Cecilia and Jose, for making this work, really work. Also want to thank the sponsors. This year we have several of them, which were crucial for funding several of the activities we have this year, like invite to speaker, tutorial, the streaming service. There is people seeing us using Zoom. So I also want to thank Pablo for being here, the dean of the faculty. Many thanks for attending the conference. So we all hope you enjoy Spire a lot this year. If you have any question, please ask us. Cecilia, Jose, and myself will be happy to help you. So, sorry. Okay. Right. Okay. So next, I'm happy to announce our first speaker today, Lena, our first keynote speaker. Welcome, Lena. Thank you for being here. Lena Salmela is a professor at the University of Helsinki with research interest in genome assembly algorithms, the Bruin graph, and other algorithms for sequencing data. Some software developed by her, such as the sequencing error correction program LORTEC, is that right? Has been used in numerous biological studies. So thank you, Lena, for being here. Her talk is the Bruin graphs solving biological problems in small space. Sorry, your slides are just coming, I think. Jose. Okay, thank you, Lena, for being here. Welcome to Chile again. This is
Okay, thank you for the nice introduction. It's actually nice to be back in Chile. So I visited Santiago a couple of times. And it seems that having Spire in Chile is good for me because I think the Santiago Spire was the only one where I've had 2 papers accepted. And now I'm an invited speaker and have one paper. So it must be good to have a Spire in Chile. But okay, so let's get back to business. So my talk today is about the Bruin graphs, and the focus will be on the applicational side. So what we can achieve in biology using this kind of data structures to solve problems. The outline is roughly as follows. So I will start with an introduction to the sort of the computational biology side for those people who are not familiar with it, and also to introduce the Bruin graphs in general. And then I will go through 2 applications in more detail. So I will talk about genome assembly and viral quasi-species assembly. And then after that, I will conclude the talk. So that's roughly what I'm planning to do here today. So let's start with the background. All of the applications that I'm talking about revolve around DNA sequencing. So, so basically, every organism on Earth does have a genome that tells how the organism looks like. And from the computer science perspective, we can kind of think of the genome just as one very long string. So that's why it fits well with the string processing conference. And then what we can do to investigate the genome is to sequence it, and that means that we can read short substrings of the genome and know what these substrings look like. They are called reads. Okay, so this is kind of a little bit idealized picture in the sense that what it really looks like in practice is this. So you don't know what the genome looks like because that's what we are investigating. And then you get your reads, but you don't know from which position of the genome the reads come from. You just have this big set of reads. Okay, so that's the general setup here. And then I'd like to go on to introduce the deep proving graph, which I'll be talking about mostly today. So a deep proving graph is a way to represent a set of the information in a set of sequencing reads. So the idea is that we have in the beginning a set of reads. This is just a very small toy example here to explain what this is about. And when we build a deep proving graph, then we first start by finding out all the k-mers, that is the k-length substrings occurring in the reads. So we get a set of k-mers. And then to build a graph, the k-mers become the nodes of the graph, and then we add an edge between 2 k-mers if they share a k-1 length overlap with each other. So for example here, TAA and AAC share the overlap AA. So that's why we are adding an edge there. Those of you who are more familiar with computer science might have come up with a slightly different definition of a deep proving graph in that context. But this is what is meant by a deep proving graph in computational biology today. I might also note that there is 2 slightly different definitions of deep proving graphs around, also in computational biology. So this is the node-centric one, where the k-mers are nodes, but then one can also define it so that the edges are k-mers, and then your nodes become k-1 length prefixes and suffixes of the k-mers. However, from a practical point of view, it doesn't really matter how you define it. You end up with very similar algorithms anyway and techniques. Then one thing to note is that DNA sequences as such is not an error-free process. So you might have sequencing errors in your reads, and then one way to mitigate that effect is to filter out k-mers that occur only a few times in the data set. Because if they only occur a couple of times, then you cannot be confident that they are actually part of the data. So what is typically done is that you only add the k-mers that occur at least some S number of times in the data set to your deep proving graph. Okay. Now we have defined the deep proving graph. It is of interest also to look at a little bit how to construct and store it. Now, this is not going to be the focus of the talk, but I just want to have a sort of a short recap of what's going on on the construction and storage side. My focus will be on the applications. But okay, so normally, if you are constructing a deep proving graph for a read set, then the first thing you need to do is k-mer counting. So this is a well-studied problem here. So you are given a read set, and what you need to do is find a set of k-mers that occur in the reads, and you also want to find for each k-mer how many times it occurs in the read set. So that's sort of the basic problem that you start with. And this is something that has been studied quite a lot. There are many good tools solving the problem. So this is sort of fairly easy to do at this point. Then in some applications, you may also want to construct the graph directly from genomes. And superficially, this looks like the very same problem as here. So basically, you want to find the k-mers that occur in the genome, but then in this case, you can trust that all the k-mers are correct because they are already in the genome. So you don't have to sort of deal with this, that you get k-mers that are not going to go into the graph, but you always know that when you see a k-mer, it's actually going to be in the graph. And then also you don't need to count them. You just need to find out which k-mers occur in the genome. Okay, so then once you have figured out how your graph looks like, then the operations that you would like to support there is the membership query, where you want to be able to tell, given a k-mer, whether it's in the graph or not. And then you want to support also navigation forward and backward in the graph. Recently, there's been also quite a lot of work on the compact representation of this data structure, and they can be sort of roughly classified into three approaches. So I can either more or less directly try to index the k-mer set, and in this area, the Boss representation is probably the most famous one. And then there are approaches where you start by figuring out the so-called unitics in the graph. So that's the non-branching paths in the deep proving graph. And this will sort of mean that you need to index shorter strings than, or the total length of the strings that you are indexing is smaller than the whole k-mer set. And a further refinement of this approach is then the simply-ticks and Euler-ticks, where you try to find longer strings than unitics that contain all the k-mers that you want to index. Okay, so I guess that's enough of this side of the story. And then I'd like to move on to the application side. So here I've listed some applications where the proving graphs have been used. So this includes genome assembly and viral class-species assembly, which I'll be talking about today. But then also the sequencing error correction methods can use the proving graphs, and you can do reference-free variant calling with the proving graphs. You can index your read sets and so on. But as I said, today I will concentrate on these two first applications, and especially I'm going to be concentrating on two solutions that use variants of the proving graphs to solve these problems. Okay, getting into the first application, so genome assembly, and I just wanted to recap this figure from the beginning of the presentation. So basically, the sequencing process gives you this set of reads, and then the genome assembly problem is then the reverse problem. So you essentially have your unknown genome here, and then you have a set of reads, and the assembly problem is to figure out what was this read, what was this genome where all of these reads came from. So you need to reconstruct the genome based on all of these reads that you have. So it's basically like a giant jigsaw puzzle to put it together, and out should come the genome in the end. Now, this is, of course, I mean, a very much of a toy example, because in reality, these strings are very long. So they, for example, the human genome is 3 billion characters long, but this is here just to sort of show that what the problem looks like in practice. Now, I'd like to start with a little bit of history of the problem, because genome assembly is a problem that has been studied for quite a long time already. So I put here sort of the most important milestones in genome assembly so far. So the first milestone here is in 2001, when the first draft of the human genome was published. And that was sort of a very huge effort at the time. It involved 20 universities and research centers, and it took like 20 years to complete. And at that time, it was sort of, especially in the media, said that, okay, here we have the human genome, but then it really was a draft. So if you looked at it more closely, then you realize that some 5 to 10% of the sequence was actually missing. So it was not a complete genome, but still at the time, it enabled a lot of new work in biology and medicine. So it was very important to have it, of course. And then over the years, there have been many refinements to the reference genome, so it's been getting more and more complete. Then the second milestone I have here is in 2010, which is now the milestone when the first large genome was assembled from the so-called short reads. And this was the giant panda genome. The significance of this is that at that point, we had the new sequencing technologies, the short reads, that were much cheaper than the older technology, which was used for the human genome draft in the first place. And the reason that this is important is that the sequencing became so cheap that it was sort of basically possible for single biological groups to look at the genome of the organism that they were studying. And that's why this is something that really sort of resulted in a lot of flurry of activity also on the method side to be actually able to assemble these reads. And then the final milestone I have here is from last year, 2021, when the complete human genome was published by the Telomere to Telomere Consortium. And again, this was not just sort of automated work. So it didn't just work so that you give the reads to the assembler and it outputs the genome, but it actually also included significant amount of manual work. And again, it was also a big effort with many universities and research centers involved. But this shows that we are getting there. The genome assembly problem, or what you get with genome assemblers, is starting to be pretty good. So it's getting closer. Now I've already said here that the quality of the end result here has sort of varied, and I'd like to next look at how the quality has evolved over the years. The most important measure for the quality of these assemblies is that how complete they are and how contiguous they are. And one might first think that you could use something like the number of contigs or the average length of the contigs being the sequences that are produced by the assembler as the measure here. But it turns out that, especially in the beginning of these works, it was not a stable measure. And the reason for this is that many of the assemblers produce a set of sort of reasonable output, but then also they produce a lot of short sequences that may be contaminants or are not really of interest. And then what people were doing, they basically put a threshold that we just throw out contigs that are shorter than this. And now you can imagine that depending on how you set this threshold, then the number of contigs and the average length of the contigs is going to vary a lot. And that's why we needed something more robust to measure the contiguity of assembly. And that's where the N50 comes in. So the way that you compute it is that you take your assembled contigs, you order them from shortest to longest, and then you find the midpoint here in terms of the total sequence length. And the length of the contig at that point, that gives you the N50 statistic of the set. So in other words, 50% of the sequence is in contigs that are longer than or equal to N50. And now you can see that if I would be adding here a bunch of short contigs, it would move this line a little bit to the left, but it wouldn't affect the N50 a lot. So that's why this is robust against this kind of changes. And now once we have the N50, then we can look at how the genome assemblies have evolved over the years. So what I'm showing here are numbers that have been taken from a number of papers that report new methods for genome assembly over the years. Now, all of these methods have not been run on the same data. So basically, what I'm showing here is the evolution, both in terms of the quality of the data that we get and in terms of the method development. The first thing maybe to note here is that the human genome is also a set of sequences. So we do have a number of chromosomes, and that means that you can compute the N50 for the human genome as well, and that's so with the purple line here. So that's the target. That's where we should be aiming at. Then the plot is divided into 5 parts. So I have the old Sanger sequencing part here. So the division is by the sequencing technologies as they have evolved over the years. And then after that came the sorted era. So that's shown here. And then since something like 2013, the long reads have sort of dominated the area. First, the PacBio long reads having a high error rate, and then more recently, the HiFi reads, which have which are long but still have a low error rate, and thus have enabled further progress in the problem. If you look back into history, then in the beginning here, the contexts were quite short, and that remained the thing also within the sorted era. Now, for these methods, I'm also showing the scaffold N50. And what scaffolds are, they are basically just contexts that have been, a set of contexts that has been ordered, and you can have a gap between the two contexts, between the consecutive contexts. So they are sort of gapped sequences that are longer than contexts, and all the technologies frequently had data that allowed you to construct these kind of things. What we can see here is that when the shortage came about, then we can clearly see the drop here in the scaffold length, and we would actually see it also in the context length if the plot would be scaled in a slightly different way. And as I said earlier, the significance of this era was not that the quality of the assembly would have gotten better. It actually got worse, especially in the beginning. But the important thing was that the sequencing became much cheaper. And then we can see that once we enter the long read era, then the N50 values of the context start to rise. And with the highly erroneous but long reads, we got to the same length as the scaffolds. And then once the error rate sort of plummeted down, then we have been starting to get better and better assemblies. And the last data point here is from a bioRxiv preprint this year, the Verco assembler, which is using HiFi and Oxford Nanopore data together. And it's almost there when you look at sort of the target where we are going at. And if you are more familiar with this work, then they actually do provide a method that pretty much gives you the whole human genome, but that's using some auxiliary data like Hi-C data or Trio data. And I chose to put here the method that is using poorly read data. Okay, so that's where we are. It's getting better, but we are not quite there yet. And okay, so far I've been talking about the human genome here because it's sort of a nice benchmark data set because we have had data for it for all of the technologies. But then maybe something to keep in mind is that the human genome is not necessarily a particularly difficult case. So for example, many of the plant genomes are significantly larger, which makes the problem harder. And then also many genomes have more variance than human genome. We humans are pretty much like cousins to each other as compared to many of the other species on Earth. So, but I'd like to say about the variance here that it's kind of a mixed blessing. In the older works where the goal was to get a reference genome, a single reference genome, it was a hindrance because it created sort of complexity in the assembly that was difficult to deal with. But nowadays people are getting more into sort of assembling all the haplotypes separately. So for example, we as humans, we are diploid, so we have 2 sets of chromosomes. And if you want to get the sequence of both of the copies of the chromosomes, then having more variants actually might help you. So there, the human genome might actually be a difficult case because we are so similar to each other. Okay, and then also, as I said, we as humans, we have 2 sets of chromosomes, but then there are, for example, many plant species that have more copies of their chromosomes, and that again makes things a little bit more difficult. And then also some of the genomes have more repetitions, and that's sort of the source of most difficulties, I'd say, in genome assembly. Last, it might be good to remember that DNA, because of like the applications in medicine and so on, DNA sequencing is often optimized for the human genome. And then when you work on some other species, then it might mean that your data quality could be lower. Okay, so that's sort of a reminder about that. Okay, I don't know what that is. Maybe it will go away. But let's get back to the sort of the method side. So how would you go about assembling a genome using a deep proving graph? So what you would do is you would first take your read set and then build a deep proving graph. And the most sort of simple and straightforward thing to do there in order to produce like longer sequences is to report the so-called unitics as contigs. And the unitics are just the non-branching paths of a deep proving graph. And in this figure, I'm showing the unitics with different colors here. So in this graph, you would get 4 unitics. Many of the assemblers do a lot sort of heuristics and other things on top of unitics, but this is sort of the basic workhorse behind all deep proving graph based assemblers. Okay. Okay, that's good. Okay, so then if you are doing an assembly with a deep proving graph, then you need to choose the K that you are using. And this is sort of a delicate choice, because if you choose a too small K, then you get a tangled deep proving graph, because you start to get collisions of the K-mers across the different parts of the genome. On the other hand, if you choose a too large K, then your graph may become disconnected, because you might have coverage problems in some areas of the genome. And then you don't have all the K-mers, or the longer K-mers from that area. Then furthermore, the optimal K may be different for different parts of the graph. So that makes things, choosing a single K also a difficult problem. And one solution that has been suggested for this is that what if we could represent the proving graphs of all the orders in a single data structure? So what could we do then? And that's sort of the variant I'm going to be talking about here for solving this problem. And here, so this kind of a deep proving graph where you put all deep proving graphs of different orders into the same data structure is called the variable order deep proving graph, and it has been introduced by Boucher et al. in 2015. So we start with a normal deep proving graph where the nodes are the K-mers and the edges are overlaps of length K-1. And then the variable order deep proving graph is basically a union of all of these deep proving graphs. But then you also need to add some edges to navigate between the different orders of the deep proving graph. So you basically need extension edges. So I'm showing here with red. The idea here is that you add an edge from a lower order node to a higher order node by adding one character, if you can get there by adding one character to the end of the K-mer. And then also you need to add connections towards the lower order graph so that you can also navigate your way there. And in this case, you basically add an edge from one K-mer to a K-1 mer so that you drop the first character of the K-mer. So that's basically what the graph would look like. But then in a normal deep proving graph, unitics are kind of a nice building block for assembly. But now you have edges all over the place here, and there's no clear definition of a unitic anymore. So that's sort of the problem that I'm concentrating on here. How do you define something that some kind of sort of unambiguous strings here that could be used as a basis for assembly, similar to unitics? But before getting there, I'd like to take a look at the variable order deep proving graph from a slightly different perspective. So if you think about the definition that I showed in the previous slide, then essentially now in the variable order graph, the nodes are all the K-mers of any length that occur in the read set. And then the edges are recapped here as well. The DBT edges are these overlaps of length k minus 1, and then the extension edges go from a k mirror to a k plus 1 mirror by adding one character, and the contraction edges go from a k mirror to a k minus 1 mirror by deleting the first character. Now, since this is the string algorithms community, then this might look very much like a suffix trie, and in fact, it is very close to being a suffix trie. So the nodes here actually correspond 1 to 1. So basically, the suffix trie nodes are all substrings that occur in the set of strings that you are building the suffix trie on. And then the extension edges are exactly the trie edges, and the contraction edges correspond exactly to suffix links. The DBT edges are not present as such in a suffix trie, but basically you get them by taking every sort of possible combination of suffix links plus a trie edge that you can sort of take continuously here. It's kind of two edge long paths in the suffix trie. So that basically means that you can use a suffix trie to represent this data structure, and since a suffix trie can be represented by a suffix tree, and further you can use some BWT based techniques to represent it efficiently. So that's where you can go to sort of have an efficient data structure for representing this. So okay, so basically here I'm using the suffix trie terminology, so using the trie edges and the suffix links, but instead we could also consider left extension, which would then correspond to a vinyl link in the suffix trie, and right contraction, which means then the reverse trie edges. And then this will actually allow for efficient implementation using a BWT and suffix tree topology. And this is actually going to be related to Diego's talk later today. He's talking about this in the context of a different application and concentrating sort of on this BWT part. But if you're interested, then stay tuned for his talk today. Okay. That went fast. Okay, here we are. Okay, so let's see let's get back to this problem of how you actually get the unitics in this data structure. So what I want to do here is now concentrate on a subgraph of the variable order graph. And I want to do it so that I only look at the nodes that have a frequency within a certain interval. And so I'm denoting the interval with L and H here. And then furthermore, I want to require that the lower bound of the interval is at least half of the upper bound. And you may ask why. What I'm giving here is sort of what is sort of the practical benefit of this, or more like why it's nice that we have this requirement here. But you also get this if you look at the sort of in a theoretical way and try to analyze how you should set this interval in order to get a contiguous and correct assembly. But I'm not going to go into the theory of that today. So let's just look why this is nice to set the interval this way. And the reason for this is that basically after that, your extensions and contractions are going to be unique within this subgraph that we define here. And if we look at this more closely, then let's consider these three k-mers here. So I have ACTT, ACTTT, and ACTTA here. And now let's just assume for a while that all of these would be part of this frequency restricted graph. And then if we consider the frequency of this ACTT, then we know that whenever this ACTTT occurs in the genome, then there must be an occurrence of ACTT as well. And the same goes for this ACTTA. So all of those must also be occurrence of ACTT. And furthermore, these must be separate occurrences because they don't share the last character here. And that means that if we compute the frequency of ACTT, then it has to be at least as high as the sum of these two frequencies. And since these are part of the frequency restricted graph, it means that they must be at least h/2. And it actually then means that the frequency of ACTT is larger than h. And that means that ACTT actually cannot be a node of the frequency restricted graph. So it's not possible to have this kind of branching in the graph, in this sort of restricted part of the graph. And then you can do exactly the same kind of reasoning to forbid the situation of having two incoming edges, two incoming contraction edges to a node. And that just basically means that whenever you're doing extension or contraction, then there's just one way of doing it and staying inside this frequency restricted part of the graph. Okay, it's really jumpy today. Okay, but this is the next slide. So then I'd like to look a little bit closer at the structure of the frequency restricted part of the variable order deproving graph. And okay, so what I showed on the previous slide, it means that the contraction paths are non-branching. So if you look at the graph in the form of a suffix tri here, so I'm showing here with blue the frequency restricted part of it, and the rest of the nodes are sort of out of this frequency limits. And then, as I said, the contraction paths have to be non-branching. So in this second picture here, so we basically have these contraction paths that are non-branching. So there's always just one incoming contraction edge and one outgoing contraction edge to a node. And then if we sort of conceptually glue together or merge the nodes inside a single contraction path, then we get these kind of structures inside or we get that the frequency restricted part of the graph is composed of these kind of structures. And that actually will give you our unique strings here. And basically, this turns into a collection of paths once you have merged together, merged into a single node all of your contraction paths that are within this frequency restricted graph. Okay, so that means that we do have a nice definition for contigs in this graph. And then what we would still like to have is an algorithm for extracting these LH sticks or these contigs as defined. And now what sort of this means here is that basically if we would do this gluing together of the contraction path nodes, then we could just like enumerate all of those. But it's sort of not necessarily very practical to do it, so we keep it sort of on a conceptual level. And then we do note that if we take any maximal path through this frequency restricted part of the graph, then that will actually spell an LH stick. And now the only problem is that there are several maximal paths that spell the same string. And the only thing that we need to now take care of is that we only spell each of those paths or each of those contigs once. And the way to do this is that we first find the set of last nodes of the paths, and these are just recognized by being nodes that don't have any outgoing edges. So that's kind of easy. In this case, this would be the last node of a path because you don't have any outgoing edges there that stay inside the frequency restricted graph. And then you basically just backward follow left extensions and right contractions as long as you can, and then you end up in the other end of the LH stick, and that gives you the sequence of the contig that you're looking for. Now this shows the process for the paths in this construction. Some of the paths can be cyclic, and that needs a little bit more bookkeeping and so on to get them out correctly, but it can also be done. So that basically concludes the part about genome assembly here. So I gave you this method that will allow you to get something like unitics or context out of a variable order deep Bruin graph. And then I'd like to move on to another application, which is also an assembly application, but it works on a slightly different kind of data. So we're looking at viral quasi-species assembly now. The difference to the normal genome assembly is that the sample that we are looking at now is contains a set of haplotypes. And I want to sort of start here with explaining what the setup is. So basically all RNA viruses, including, for example, HIV, they do have a high mutation rate. So it means that if a patient gets infected with the virus, then they start sort of with the one sequence of the virus, but as the sort of infection goes on, then they do develop different kind of mutations and recombinations that leads to a population of viruses with different haplotypes. So we end up in a situation like this. So in this case, there would be like 4 different dominant haplotypes there, and the different haplotypes may also have different abundances in the sample. So in this case, the first haplotype here is the most abundant one, and then the rest of them are a little bit less abundant. And then we are calling this population of related but distinct haplotypes the viral quasi-species. And if we look at the assembly problem, then the idea again is that we do have a set of reads produced from this sample, and then what we would like to figure out is that what is sort of the haplotype structure inside the sample that we are looking at. So, okay, so basically we are given sequence reads from a viral quasi-species sample, and we want to assemble this part. Here I'm considering the de novo variant of the problem, so that means that there is no reference sequence available, or we are not using it, so it's either not available or we just somehow want to avoid reference bias and thus are not looking at the reference sequence. But that's just sort of the setup of the problem. And another assumption I'm making here is that the sequence reads are Illumina paired reads. So that basically just means that they are fairly short reads and they do come in pairs as shown here. So you always get like 2 reads and then you don't know the approximate distance between the reads. And this is sort of further information that we can use in the assembly. Okay, so that's the setup. And then I'd like to introduce another variant of the deep Bruin graph that we've been using to solve this problem, namely the paired deep Bruin graph. This was first introduced by Medvedev and others in 2011, but so we used it in this work, but we also sort of did modify it a little bit to make it fit better the viral quasi-species problem. The idea here again is that we start with the deep Bruin graph built on the whole data set, and then we add the paired information on top of this graph. So basically, the idea is that the reads come in pairs like this, and then for each k-mer here, which would denote a k-mer in the first read in the pair, we look at the corresponding position in the second read, and then we add these k-mers as paired k-mers in this graph. So the idea now is that after looking at these pairs, we have a graph that is basically the deep Bruin graph, but then also we have these links that tell what are the sort of paired k-mers in the other pair of the reads where the k-mers occur. So basically now our nodes of the graph are pairs of a k-mer, and then all of the paired k-mers that we got from the read data. Now, if we look at this structure here, this example structure, then it's kind of apparent that these k-mers here, they link to this kind of structure which has sort of 2 paths here. But the k-mers have links to both of these paths. And that sort of suggests that this probably should be split into two, because they occur in two haplotypes in our case, due to the fact that the paired reads suggest that there are actually two paths that they link to. And then the problem becomes that we need to split these nodes by clustering the paired k-mer set. And this is sort of here. And then furthermore, we are now processing two adjacent nodes at the same time, because that will allow us to process the edges correctly as well. And let's now take a closer look at how we resolve a single edge. So there's been several suggestions how to do this. So in the original work by Medvedev et al., they just said that they want to cluster the k-mers so that they sort of cluster all the k-mers that are reachable from each other into the same cluster. And this sort of made sense in the assembly, in the genome assembly world, because there the assumption was that there were two k-mers that were sort of collapsed together, but they came from very different parts of the genome, and then the paired k-mers hopefully would be like totally separate in the graph, and that then would result in this kind of problem, that you assume that if the k-mers are reachable from each other, then they are sort of part of the same, from the same part of the genome. But this is not quite good for the haplotype assembly problem, because then the typical thing is a structure like this. So you have your collapsed k-mers here, and then there are two different haplotypes in the viral data, which gives you this kind of structure, that they share maybe the first nodes here, but then there are different nodes here because there is some kind of variant in the sequence. And then with this definition, this basically says that all of these k-mers are reachable from each other, although you have to reverse sort of the direction here. And that means that we needed to slightly modify this definition to make it suitable for the haplotype assembly problem, or viral quasi-species assembly problem. And we actually had two different ways of doing this. We started out with looking at the reachability graph of k-mers. So we were just looking at which k-mers are reachable from each other, either using only forward edges or only backward edges. So in that case, for example, this k-mer here would not be reachable from here, because you have to sort of first go backward and then forward on the edges. But then all of these would be reachable from each other, and all of these would be reachable from each other. So the basic idea was that we just create the reachability graph and then find the clicks in the reachability graph. But then later we thought about this problem a little bit more carefully, and came up with the fact that actually the clicks are an approximation of what we want to do. So what we really want to do is to find the strains here. And that then corresponds to finding a path cover on this part of the graph. But in both cases, the aim is to get these splits so that basically all of the paired k-mers that are on this path are sort of linked to a single copy of this split node here, and then the ones that link to this lower path are then put into this second copy of the nodes. Okay, so this is basically what we've been doing in this problem, and I'm showing here then the sort of very high level view of the complete process in these two publications that we've been working on when it comes to the viral quasi-species assembly problem. So in the VIA-DBT paper, what we did was we first error corrected the reads and then update the solid k-mers. Then we built a paired de Bruijn graph, and this was using the click approach. And then we extracted the haplotypes as unitics of the resulting graph that we had after adding the paired end information on the de Bruijn graph. And then the second version of this work was to just obtain the solid k-mesh in a slightly sort of more clever way, so that we didn't have to do the error correction first, and then building the paired deep proving graph and using this path cover problem to build it, and then also in the extraction of the haplotypes, and in the phase where we extract the haplotypes, we were using mean cost flow and linear programming to get a sort of better estimates here. And I'd like to conclude this part by showing some experimental results. So these are results for a benchmark data set on HIV virus. And this is sort of a nice benchmark data set in the sense that it gives you a ground truth, but it's still a real data set. So how this has been produced is that they have taken 5 HIV strains and the actual DNA molecules of them, and then they have mixed them in a test tube and finally sequenced with Illumina. So that means that we know what went into the test tube, and we still get sequencing data that is real data. And this basically shows the characteristics of the data set. So the HIV genome is a little bit less than 10,000 base pairs long. The data set has a high coverage. There are the 5 haplotypes, and the abundance of the different haplotypes varies from 10 to 30%. And then if you look at the haplotypes pairwise, then the divergence is between 1% and 6%. This means that on how many positions the 2 haplotypes would differ from each other. So that's what the data set looks like. And then the next slide shows that what kind of accuracy we can achieve. In this case, I'm showing here a comparison to 3 other methods. Virus VG and VG flow are based on overlap graphs, for those of you who know the technology or the method. And then p-haplo is another deep proving graph-based tool, but it doesn't use the paired deep proving graph method that we are using. And then these are our tools. And now if we look at the results in a little bit more detail, then the first column here shows the genome fraction. So that basically tells us what fraction of the 5 haplotypes we were able to retrieve from the data. And so now, for example, virus VG has here a genome fraction of slightly over 80%. And if there are 5 haplotypes, then each of them is responsible for about 20% of the end result. And this is starting to be so low that we are suspecting that there might actually be a complete missing haplotype in this case. Then if we look at the error rate column, then it's worth noting that if the error rate starts to be in the same ballpark as the divergence, then that probably suggests that there are mixed haplotypes there. Because then when you compare the reconstructed haplotype to the real haplotype, and if it's a mix of 2 haplotypes, then basically it means that the part that is aligned to the wrong haplotype will have a divergence or error rate that is close to the divergence. So that's what we are suspecting that is going on here. Okay, so we were here, and then finally there is the N50 column, and sort of like a conclusion here is that the overlap-based methods here give a high N50, but as we saw, they have some errors. And then for our tools, we get a low N50, but then much less errors. So in that sense, it's more correct, although it's not quite as long. It's of course worth noting here that there is some kind of trade-off between the N50 and the error rate here, because you can always produce longer sequences if you don't care whether they are correct or not. But I think in biological terms, it's nice to be able to put the error rate low, because biologists don't necessarily appreciate it if you just give them some results that may or may not be correct. And then finally, we also looked at the sort of runtime and memory usage here. And now this shows what you in a typical case, get with the deep Bruin graph-based method. So the runtime is way smaller than for the overlap-based methods, and then also our memory usage is very small as compared to computing the overlaps. Okay, so then I'd like to move on to the conclusions. So I have talked about the deep Bruin graphs here and shown that they are sort of a nice data structure to represent the information of a large read set in a small space. And I talked about two applications here, the genome assembly and the viral quasi-species assembly problems. There are also many other problems where the data structure is useful. And then there are also many variants of the deep Bruin graph that have been developed. Here I talked about the variable order deep Bruin graph and the paired deep Bruin graph. Finally, I'd like to acknowledge my colleagues for the work that I'm presenting here. So the viral quasi-species assembly work is joint work with Borja Freire, Susana Ladra, and Jose Parama from University of A Coruña. In particular, Borja has been doing most of the implementation and experiment work in that part. Then the LHDX and the variable order deep Bruin graph work is joint work with Diego Diaz and Simon Puglisi from University of Helsinki, and also with Takuo Nodera from University of Tokyo. And finally, I'd like to acknowledge my funding. So I'm grateful for the funding from the Academy of Finland. Thanks, and I'm happy to take questions if you have any.
Okay, thank you, Lena. We have like 10 minutes for questions. Any question from the audience? Yeah.
So you mentioned and motivated the creation of VOD because the K for creating the Bruin graph is not easy to choose. Can you give some intuition on the quality of LHTX compared to UniTX?
We've done some experiments, and I think we are getting a little bit longer context than what you get with UniTX, and we are currently still working on the experiments. That's why I don't have too much of them on the slides. But there is a preprint available on bioRxiv on this work if you are more interested in it.
So actually, I'm gonna. This is relevant to something I'll be saying at the end of the day, but so I remember Simon gave a talk at SAB, and he was talking about doing the navigation. So he said that the degrees, like navigating the degrees, representing the degrees in BOSS, this was done not badly. It wasn't done very well. Jarno has been speeding that up, but I got the feeling that was only working for the fixed K. Do you know if the stuff Simon and Jarno were doing can also do the variable K?
I think they have been working with a single K implementation. Okay. That's my understanding.
Okay.
Okay. Of course, I'm not really involved in that work, so that's what I know.
Okay, because I also don't know, but I got the feeling it was just a single K. I was just asking if it's also related, if Simon's porting it into this LH stuff. Okay.
Not at the moment, as far as I know.
Thank you.
Okay. Any other question? Okay.
I have a very basic question, a very interesting talk. I'm an outsider here. So at the beginning, you said that you delete infrequent k-mers.
Yeah.
There is some. So I suspect errors are equally likely, or that's not true?
In most of the technologies, one can assume that they are sort of random errors. There are some errors that are more likely to occur. For example, the Illumina reads mainly have substitution errors, so they don't have that much insertion deletions, although they can have a little bit of them as well. And if you look at the sort of the profile of the long reads, then the insertion deletions start to be more frequent than substitutions, but still in PacBio, they are more or less
Random.
random.
Okay.
But then in some of the other technologies, like the hi-fi rates, a typical error is sort of that you misestimate the length of a run of symbols. So then you can do something based on knowing that that is the typical error.
So assuming that the errors are random, deleting all the infrequent k-mers, it implies that if there is something interesting, there is one outlier, you will never see it.
Okay, so if you are doing genome assembly, you sort of assume that you have a fairly good coverage of the data. So you are assuming that you will see the same site several times inside the data. And then if you only see it once, then it's usually an error.
Okay.
Of course, you can have a sort of some cases where the coverage is low for some part, for some reason. And then, of course, this doesn't work.
But you don't know the coverage in practice, right?
In practice, it's usually pretty good. So I think this works fairly well in practice. But then if you work on some other applications like variant calling, where you might have lower coverage, then this becomes an issue that there can be something also in the sole k-mers. But then only if you see it once, then there's a significant uncertainty whether it's real anyway.
First, thanks for the presentation. I have just a small question about the different numbers of K.
Yeah.
How, I mean, do you have any idea of what's are the numbers of the range? What is best, or if there is any relationship between these values in different organisms, or is it the same? Do you have any?
Yeah, so this problem of choosing the value of k, there's been work studying it. So, and it's not a simple thing to do. It usually depends on the data set. Depending on what you are doing, I'd say for many applications, something like 32 would work reasonably well. But then if you want to do assembly, for example, then the longer k-mers that you are able to use, the better the result usually is. I mean, of course, at some point you arrive at an upper limit where you cannot increase it anymore because the graph becomes disconnected, as I said in this talk. So, but with many other applications, actually shorter k-mers sort of suffice to give you a reasonable answer.
Okay, so my question was because how do you know whether you are using the right values, right? I mean, do you have any feedback about the results or the topology of the graph, or I don't know. Do you have?
Yeah, I think, I mean, if you are using an assembler that uses a single value of k, then what people usually do is that they run the assembler with different values of k, and then they somehow measure the output. I mean, N50 is one of the measures that you can use to see how contiguous it, but of course it doesn't tell much of the correctness of the assembly. So that's one thing. Then there are some assemblers that sort of work in an iterative manner, so that they start with a low value of k, and then they do several rounds of assembly and increase the k in every round.
Okay, and just one more question about the k-mer representation, because you are talking about just k-mers or canonical k-mers, or do you have any idea of these other kind of representations like minimizers or?
Yeah, okay. So most of the applications in practice use canonical k-mers because you don't know whether the k-mer comes from the forward or the reverse strand. I didn't sort of want to put it in the presentation because it's kind of a detail that maybe complicates things a little bit too much for this kind of presentation. But okay, so the canonical k-mers are like you take a k-mer and its reverse complement, and you only store the smaller of these ones, which saves pretty much half the space in these representations. Then I think many of the unitic-based representations for deep Bruin graphs use minimizers to store the unitics and to be able to sort of like index them in an efficient way. So they are certainly used there. Yeah, or you have maybe a different k value for the minimizers. Yeah.
Hi. When the crossover happens between diploid or multiploid species, it doesn't happen uniformly at random in a sequence. It has hotspots, which have a different probability, which evolve among generations, the probability of the hotspots and so on. And you mentioned that when you do the graph, you have to take into account the number of chromosomes, which are not connected and so on, and you're working with all the data with it. But I was wondering, if you have hotspots, then the fragments between two hotspots, they will be building some words which will be very frequent and which should appear in the graph. And if you have some knowledge about those hotspots, it should make the graph more typical and maybe easier to build. But I was wondering if that's an idea for in the next revolution in 10 years, or if some people were taking advantage of it. The reason why I think it might be very relevant is that you mentioned that plants had sometimes 4 different copy of the same chromosome. But in my experience, they will have variation, but also a lot of fragments identical. And understanding the hotspot might help to put a structure. If you have not just 2 chromosomes, which might be variant, but 4 or 6, I think the hotspot will maybe be important for that. But I'm curious if it's already done or if you have any intuition about it. Does it make sense first? Because maybe it doesn't.
I'm not aware that somebody would have considered that. That of course doesn't mean that it hasn't been done, but I'm not aware of that. Then whether it would be useful or not, it's hard to say. Maybe for some applications it would be useful to somehow consider it.
If you have hotspots, the graph will have long sequences, non-branching nodes.
Yeah, that's true.
So if you have a very far away hotspot, or very few hotspots, to take an extreme theoretical case, if you have very few hotspots, then the graph is much easier to build.
Yeah, that's true. Yeah, and it's going to be much easier to assemble the parts that are between these hotspots. Yes, that's true.
Okay, questions from the people attending online? Is there any question? Okay, no question. I have a quick question, data structure question. You say that to support these navigations on the variable order degree, the Bruin graph, you can use suffix links and triages, or binary links and reverse triages, right?
Yeah.
Is there any difference in terms of functionality or efficiency? How do you choose what to use?
Well, basically, I mean, if you're using BWT, then you can sort of easily support one direction.
Okay,
if you want to support both directions, then you need to do some extra work to get it done.
Okay.
And well, I guess it doesn't really matter which way you support, because you can take the reverse of your strings if you want the other one that you're not supporting. Yeah.
Okay. Any other question? Okay, let's thank Lena again. I have a present for you from the organization. So this is for you. Thank you.
Thank you.
Okay, I think we have a coffee break now. Okay, and 15 minutes before the next session starts. Thank you.
Actually, again in 10 seconds. Yeah, lots of stuff. I ask about it. I should go right now. I'm just trying to get my student to present this. So I should go and see this is what's on my yeah. So she doesn't.
Wanna leave my old life behind. Not an answer, not a follower. Fit the box with the mold, have a seat. Yeah, take a number. I was lightning before the thunder. Thunder, feel the thunder. Lightning and the thunder. Thunder, feel the thunder. Lightning and the thunder. Thunder. Kids were laughing in my classes while I was scheming for the masses. Who do you think you are? Dreaming about being a big star. They say you're basic, they say you're easy. You're always riding in the backseat. Now I'm smiling from the stage while you were clapping in the nosebleed. Thunder, feel the thunder. Lightning and the thunder. Thunder, feel the thunder. Lightning and the thunder. Thunder. Thunder, feel the thunder. Lightning and the thunder. Thunder, thunder, feel the thunder. Lightning and the thunder. Thunder, thunder, feel the thunder. Lightning and the thunder. Thunder, thunder, feel the thunder. Lightning and the thunder. Thunder, thunder, feel the thunder. Lightning and the thunder.
It's been a long day without you, my friend, and I'll tell you all about it when I see you again. We've come a long way from where we began. Oh, I'll tell you all about it when I see you again. When I see you. tripping over myself, aching, begging you. Thought we were bigger, pushing each other to the limits. We were learning quicker. By 11, smoking herb and drinking burning liquor. Never reached, so we were out to make that steady figure. Once I was 11 years old, Daddy told me, get yourself a wife or you'll be lonely. Once I was 11 years old. I always had that dream like my daddy before me. So I started writing songs, I started writing stories. Something about that glory just always seems to bore me. Cause only those I really love will ever really know me. Once I was 20 years old, story got told. Before the morning sun when life was lonely. Once I was 20 years old. I only see my goals, I don't believe in failure, cause I know the smart.
Hi, Nadia. We can see you online.
Can you hear me?
Okay, yeah, I can hear you very clearly. Yeah, we are in the coffee break right now, so we will be here in like 2 or 3 minutes, right?
Okay.
Okay, thank you. I will let you know anyway.
Yeah, so they actually, so they kept going with that, and they had a lobby paper. I don't know if you, is it, Adrian and Andre?
Yeah, I did not finish the work with that. I saw that in the WCT, there is a paper with you and that.
Yeah, but that's something else. Actually, that's like, so they were doing this online. It didn't, like, they got the lobby paper. It doesn't really work yet. And now we have an alternative that we maybe I will keep it on the so yeah, that's the thing going on. Oh, so you have a paper. Yeah, I saw that. But no, it's in it's up. So they have the like some people that
I think we can check. And you have to use the microphone just for the stream. Okay. But they have right, but there's one. We put in the front. Yeah.
is it there? No.
Yeah, that's okay. The problem. The biggest one. So it's not yeah, that will be so the moment my suggestion is for now just yeah, yeah.
Certainly it will be working.
Yeah, that's what I mean. Right. We're going always with the process.
Yes, let's start. But if you haven't had any disasters yet.
Yeah.
That's gonna be.
Yes.
Where are you now? Were you only imaginary? Where are you now? Venice. Under the sea, under the sea. Where are you now? Another dream. The monsters running wild inside of me. I'm faded. I'm faded. So lost. I'm faded. I'm faded. So lost. I'm faded. These shallow waters never met what I needed. I'm letting go, a deeper dive, eternal silence of the sea. I'm breathing alive. Where are you now? Where are you now? Under the bright but faded lights, you set my heart on fire. Where are you now? Where are you now? Where are you now? Venice, under the sea, under the sea. Where are you now? Another dream. The monsters running wild inside of me. I'm faded. I'm faded. So lost. I'm faded. I'm faded. So lost. I'm faded.
I'm not afraid to let go. You decide if you're ever gonna let me know. Yeah, suicide if you ever try to let go. I'm sad, I know, yeah. I'm sad, I know, yeah. Who am I? I'm not afraid to let go. You decide if you're ever gonna let me know. Yeah, suicide if you ever try to let go. I'm sad, I know, yeah. I'm sad, I know, yeah. I gave her everything. She took my heart and left me lonely. I think broken hearts contagious. I won't fix, I'd rather weep. I'm lost and I'm found, but it's torture being in love. I love when you're around, but I fucking hate when you leave. I'm not afraid to let go. You decide if you ever gonna let me know. Yeah, suicide if you ever try to let go. I'm sad, I know, yeah. I'm sad, I know, yeah. Who am I? I'm not afraid to let go. You decide if you ever gonna let me know. Yeah, suicide if you ever try to let go. I'm sad, I know, yeah. I'm sad, I know, yeah.
Okay, Nadia, people is coming back to the room, so I think we can start. Okay, Nadia, are you hearing us? Nice. Okay, Nadia, we're done. Nadia, we can see you now. Can you hear us? Nadia? Hi, Nadia?
Yes.
Okay. Now we can listen to you. Okay, we can start now.
Okay. Is the speaker ready? I cannot see the room.
Yep.
Nor the screen.
Yes, I'm ready.
Okay. So, welcome to this session of Spire. I'm sorry I cannot attend in person, so I have to chair online. So we start with session 1, computational biology. I'm very happy to chair this session and thank the organizer for all their work. And the first speaker is Lucas Ramos, who will talk us about genome comparison, succinct colored brain graph. And this is a joint work with Felipe Luza and Guillermo Telles. Please, Lucas.
Yeah, thank you. Okay, so hello everyone, good morning. I'm going to present the paper Genome Comparison on Succinct Color Different Graphs, which was developed by me, Felipe Lousa, and Guilherme Telles. So let's start with a few motivations, if this works. It's just... Okay, I guess I have right now. Okay, so the improvements in sequence technologies have increased the volume of genomic data available And assembling a complete genome, obtaining a single sequence for each chromosome is still a hard problem. So in this work, we studied if it was possible to compare a set of genomes directly from their deep brain graphs without assembling them or even extracting paths from them. So we start, okay, this is not working again. Okay, now, okay, the delay. Okay, so let's start with the background. So the main data structures that we used in this work are based on the Borosian transform, or the BWT, which is a well-known reversible transformation. And with the BWT, we can do string comparison using the Burroughs-Wheeler similarity distribution, which computes similarity measures between strings using the BWT. So let scat be the concatenation of two strings, S1 and S2. The more the symbols of S1 and S2 are intermixed in the BWT, the greater is the number of substrings shared by them. So the BWSD between S1 and S2 is this probability mass function. And with this probability mass function, we can compute distance measures as expectation and Shannon's entropy. Okay, so here we have an example for the strings S1 abra $1 and S2 cadabra $2. Here we have the BWT over the concatenation of them. Then we have the alphabet vector, which represents from which string each character came from. Then we do a run length encoding of alpha. So for example, here we have 3 occurrences of a character from string 2, and it is represented by this exponent 3 here. And then we have the values of cheese, which basically represents how many times each exponent appear in the run length, and also the size of the run length. And with these variables, we can compute the probability mass functions and compute distance measures as the expectation and entropy between these two strings. And in this work, we are interested in comparing genomes, and we are going to represent them using the Braun graphs. So for example, down here, we have this string collection here, and the k equals to 3. So a Braun graph for this collection is a graph containing a unique k-mer, a unique free-mer for each node in S, and also an edge between a overlap of size k-1 between the suffix of a vertex u and the prefix of a vertex v. So for example, here we have the k-mer or the 3-mer TAC, which occurs in these two strings, but it's represented uniquely here in this node TAC here. And the overlap between TAC and ACA, for example, produces this outgoing edge here, while the overlap between TAC and ACT produces this outgoing edge here to this vertex. And since we are interested in comparing genomes, we are going to extend the original formulation of the Braun graphs for a union graph, which is the color Braun graph, where the identification of each collection is provided by coloring those edges present in the collection. So here I split the last collection in these two collections. Then we have the Braun graph for collection 1, the Braun graph for collection 2, and then the union graph, the color Braun graph of S1 union S2. And here we can have, for example, these parallel edges, which are edges that occur in both the Braun graphs here. And here we can also observe that since storing a Braun graph is not space efficient, and to space efficiently store this graph here, we're going to use the Boss representation. So basically here we have that same Braun graph for that collection. And if we colexographic order all the k-mers from this Braun graph into this node conceptual matrix that we do not actually need to store, we can get the outgoing edge of each one of these k-mers into this W string. And this W string, together with this W minus bit vector, this last bit vector, and this C frequency array, we can represent this Braun graph and also navigate and do some operations on it. And that's the background. So we can go to our method, which is the GCBB algorithm. So we propose this algorithm that does genome comparison using the Boss representation and the BWST. So the input is a set of genomes S. Each one is a collection of reads in a FASTQ file, as this one, where we are interested in the sequence here in orange, and also the value of K to construct our de Bruijn graphs. And the output of our algorithm is the matrices DM and DE containing the expectation and entropy between all pairs of genomes in the collection. And we divide the GCBB in 3 phases. Sorry. So in phase 1, we compute some structures. So we have the LCP, the BWT, and the CL array for each genome in the collection, where CL is just a context length array that I will show later. Then we are going to merge these arrays for each pair, generating a document array. And to do that, we're going to use the eGap algorithm to construct and merge these arrays in external memory. So for example here, for the genomes S1 and S2, we have the BWT, LCP, and CL for S1, the BWT, LCP, and CL for S2. Here we have the context, just to keep track from which suffix each value here came from. And then we merge these arrays into these merged arrays, generating a document array, which represents from which genome each value here came from. And with this constructed and merged arrays, we can go to phase 2 of our method, where we are going to do the actually boss construction. So the boss construction, the boss can be constructed in linear time, as proposed by Ejiji et al., just using the BWT and LCP arrays. And we extended this by adding a color speed vector to the boss construction. So for example, here we have the color speed vector that represents from which genome this chimer with this outgoing edge happened. We also added this coverage information array, which represents how many times this chimer with this outgoing edge happened in this genome here. And we also have some extra longest common suffix and chimer length summarized arrays here, which are used in phase 3. So with this colored boss constructed here, we can go to phase 3, where we're going to do the BWST computation between these 2 genomes. So during the BWST computation, we are interested in comparing chimers. So we are going to filter those edges where KL was smaller than K. I colored this in red here. And now we have this filtered colored boss, which represents both the genomes S1 and S2. And this color speed vector here can be used in the BWST computation as that alpha array from its definition. So here we have the alpha array, then we do a row length encoding, we get the values of T's and S, then we have the probability mass functions, and then we can compute expectation or entropy between S1 and S2, the genomes. And in this example, we did not use coverage information. And how can coverage help in this BWST computation? So from the BWST similarity, from the BWST definition, its similarity increases when we have more intermixed values in the BWT. And from the de Bruijn graphs and the boss definition, after constructing the colored boss, the edges from 2 equal chimers with equal outgoing edges from distinct genomes will always appear in the alpha array as 1, 0 followed by 1, 1. So for example, this ACT with outgoing edge C here, these C's will always appear as 1, 0 followed by 1, 1. And it does not depend on the number of times it happens on genome 1 or genome 2. But if this happens a lot of times in genome 1 and genome 2, this should say something to us. So to exemplify that, I added this, I increased the genomes here with this ACTC string here, 3 times here and 2 times here. And after doing all the arrays construction, the merge, the colored boss construction, and filtering the edges where KL was smaller than K, in this case 3, we obtain this filtered color boss. And these 2 last rows here represent this chimer ACT with outgoing edge C from genome 1 and from genome 2. And here we have that coverage, the number of times this chimer with this outgoing edge happened in the genome. And again, the colors will be this alpha C array here. But in these two last positions, instead of adding 0 with exponent 1 and 1 with exponent 1, we are going to add the coverage, since we have the same outgoing edge from the same chimer from distinct genomes. And this will not necessarily increase the similarity because we do not have more intermixed values. So we are going to expand this run length in a way that we have more intermixed zeros and ones as long as we can, as far as we can here. Then we have the values of t, s, the probability mass functions, and the expectation and entropy, which you can observe is very distinct from the one without considering the coverage information, but we are going to see this better now in the experiment session. So we implemented GCBB in C, and it can be accessed through my GitHub, and we evaluated it by reconstructing the phylogenetic trees of the Drosophila species. We ran GCBB for k equals 15, 31, and 63, with and without considering the use of the coverage information. Then we used the neighbor joining algorithm to reconstruct the phylogenetic trees from the distance matrices produced by GCBB. And finally, we used the Robinson folds distance to compare our phylogenies with the reference. And we also limited our experiments to 48 gigabytes of RAM. Okay, so here we have the dataset information over the genomes that we used. So all the genomes here were sequenced using Illumina NextSec 500, except for the Drosophila green-shawi here, which was sequenced using the method mini-ion. And here we have the information over the data structures construction. So we have the BWT, LCP, and CL size for each one of the genomes and the time to construct them. And just as an extra information, the longest merge between two genomes took 6 hours. And to construct a colored bus for a pair took an average 1 hour. And to compute the BWSD for a pair took an average 2 minutes. Okay, so here we have the Robinson folds distance matrix between our phylogenies and the reference, where 0 here means that we have the same phylogeny. So here in the left, we have the reference phylogeny that we aimed to get here. So up here we have the Melanogaster group, then we have the Ananasi group here, and then we have the remaining genomes down here. So we have the Obscura group here and the remaining genomes down here. So I'm going to start analyzing the phylogeny produced by GCBB using the entropy distance matrix and k equals 15 without considering coverage information. Here we observe that we already have some correctly together genomes as Jakub and Erecta here, or these genomes in this subtree here, but we have some inconsistencies, as for example, Virilis here, which is in the wrong subgroup because it should be down here, and also like Ananasi here, which should be outside the Melanogaster group, and it's inside here. And when we add coverage information to our experiments, we fix some of these problems. So now we have the Melanogaster group correctly segregated here, Ananasi group also correctly segregated here, and down here, the biggest problem that we have is that the Obscura group down here should be closer to the other groups up here. And when we increase the value of k to 31 and keep the use of the covered information, we fix one of these problems, which is the Obscura group here. And now the only thing that is wrong with our tree is that green-shawi here is swapped with Drosophila virilis here. But it's almost a perfect phylogeny here. And during our experiments, we also studied the effect on data size. So we changed that Drosophila green-shawi with Drosophila green-shawi sequenced with Illumina HiSec 2000, where we had considerably less sequenced bases and a considerably smaller average LCP and maximum LCP. And in this case, we observed that when we had a considerably different size amount of sequenced bases, we did not get so good results. And okay, so now we have the conclusions here. So the method shows promising results to compare genomes directly without assembling them. We observed that the use of the coverage information reduced the Robinson-Fold distance in most cases. And we also observed that limitation when there are significantly different volumes of sequenced bases. And as future work, we could investigate different strategies for dealing with coverage information, since we tried just one, and also the use of the quality of the sequence bases from the FASTQ files, which we did also not use. We just got the FASTQ files and directly built the different graphs, the post-representation, and compared the genomes. And that's it. Thanks, everyone. Muchas gracias. We also thanks Professora Marinella and Professor Nalva Almeida and the funds that helped financially this research. Thank you very much.
Thank you, Lucas. Perfect timing. We have room for a few questions.
Thank you.
I do not see any in the chat. I don't know if they are in the room, but I have mine in the meantime. My question is, how do you pick the K, the value of K? How did you do that in your experiments, and how in general do you think this should be done?
Okay, so first we just try to use those different values of K that we use, like 32, 64, and 100, and 32, 64, and 16, right? Or 15. So we basically saw that we had a, like, we also had the average LCP and maximum LCP of the reads that we built the structures. And we saw that after passing the value of K of the average LCP, we got some better results. So that was the way that we use it to select this K. But as we saw in the first speak here, selective value of K is always a problem in these assembling problems, right? So that's
okay.
That was the way that we used it to select it. Just test a lot, and we think that closer to the average LCP was a good fit for the K.
Okay, okay. Other questions from people in the room?
Yes. Hi,
Please.
Nadia. It's Juja.
Hi. Hi, Juja.
Thank you for a very interesting talk. I have two questions and one comment.
Okay.
The comment, just very briefly, I think I wouldn't call, when you compared the two phylogenies at the end and you said they were almost the same, I would be careful and not call them perfect phylogeny, because that, as you know, has a different meaning in the context of phylogenetic reconstruction.
Mm-hmm.
The two questions are, so I know the paper that you're referring to by Mantacci et al. About the distance measures based on the BWT, and I think I'm sorry, I just missed where the difference is. So what you're doing now to what they're doing in that paper?
We are actually just using their idea of the Burroughs-Wheeler similarity distribution, but our paper was more as a proof of concept, or of comparing the genomes directly from their different graphs from the raw reads, let's say. Like, it's just we just combined a lot of data structures. So we had the BWST, the post representation, and we studied if it was possible to compare them just using the post representation.
And you are literally using their measure, their distance.
Yes,
one
yes.
of the three distance measures.
Yes,
okay,
that's right.
Okay, and then the other question I have. Again, I probably just missed it, but when you were comparing those trees, those phylogenetic trees, I didn't see where the Robinson-Fold distance was, because I saw you explaining what was wrong with the tree on the right, but the Robinson-Fold distance is just a number, no?
Okay.
Isn't the argument that it gets better as you add coverage information, or the number gets lower, but where was the number?
Okay, I'll probably forgot to show, but up in the presentation, I had the Robinson-Fold distance matrix, and I was like coloring the cells of the phylogeny that I was talking about here. So in the left, we always had the reference, which is from a paper that reconstructing the Drosophila phylogeny. And in the right, I was switching the phylogenies that we produced using GCBB.
Oh, that's like that 16C and
yes,
right,
yes. So I
okay.
started.
These are different versions of your.
Yes,
okay.
Okay. So each one of
Right.
each one of that cells represented a distance matrix.
And the two rows are one are.
So.
Okay.
Okay. So here we have each one of these values represent a distance matrix.
Yeah.
So here we have the distance matrices obtained using entropy. So, okay, so here we constructed the colored boss using k equals 15, and we computed the BWSD and the entropy from the BWSD without considering that coverage information like intermixing the edges and so on. And here it's the same, it's the distance matrix from the entropy with the BWSD computation using the boss construction with k equals 15 and considering the coverage during the BWSD. Sorry, I wasn't
so
really.
Those numbers in the table are the Robinson-Fold distance.
Yes,
okay.
And the numbers here are the Robinson-Fold distance.
Okay,
and here are the values of the case of the constructed bosses. Sorry, I was not clear.
Thank you. Very interesting. Thank you.
Okay. Thank you very much for the questions.
Okay, thank you, Lucas. I think we should move on to the next talk. Thanks to the speaker.
Okay, thank you. Thank you very much.
Next presentation is for the paper Katka, a Kraken-like tool with K given at query time by Travis Gage, Sana Kaskuli, and Ben Langmead.
Hello, everyone.
Please.
Okay, so I'm going to share my screen. Can you see my screen?
Not now, yes. Yeah.
Okay. Hello everyone, my name is Sana Kashkuli. I'm a master's student at Dalhousie University, and today I would like to present Katka, a Kraken-like tool with K given at query time. This is a joint work with my supervisor, Travis Gage, and Ben Langmead, professor at Johns Hopkins University. So the word Kraken refers to a mythical sea monster that is very huge, and you might wonder what does it have to do with this topic. So we're going to find out in short. So Kraken is a tool for metagenomic analysis and taxonomic classification, and it is widely used in bioinformatics. So given a phylogenetic tree and an integer k, it indexes t such that later, given a pattern of length m, it can quickly report the root of the smallest subtree whose genomes contain all the occurrences of the k-mer in the phylogenetic tree. So how Kraken works is that at construction time, we give it integer k and it builds a k-mer index. So for the 9 distinct k-mer that we have here, for each one, it stores the root of the smallest subtree that contains all the occurrences of that k-mer. So for example, here, if we, I don't know if you can see my pointer.
Yes, we do.
Okay, great, thank you. So if we consider this k-mer ACA, it will return, it will actually store the root of the smallest subtree, which is 2, that contains all the genomes that have the occurrence of CAT, which is genome at node 1, genome at node 3, and genome at node 5, which they have CAT. But these 2 genomes, they don't have it, so it is actually a correct value to be returned. So, as I mentioned before, Kraken is very popular, and it is used to get reads or the origin of the genetic material and tell where it belongs in the tree of life. But Nazca et al. Showed that the database composition strongly influences the performance. So if we add more data, the roots of the subtree it reports tend to get higher and higher in the tree, and we need to make a K larger. That would be fine, except that if the representation in the data set is skewed, some of the subtrees of the tree of life are heavily represented and some others are not. So then we would want to have a large K for the subtrees that are heavily represented and a smaller K for those that are lighter. So of course, we can have lots of different values for K, but this is where the picture that we saw at the first of the presentation would be very relatable, because then Kraken would be very large. So the observation is that we don't really need the exact index, because there can be like another appropriate approach. So if we can find the first and last genome in the phylogenetic tree that contains the K-mer, then we can use an LCA query to find the root of the smallest subtree whose genomes contain all the occurrences of the K-mer in the phylogenetic tree. So we can find the last genome in the tree that contains a K-mer, and it will be equivalent to finding the first genome in the reversed version of the tree that contains the reverse of the K-mer. So we're going to focus on finding just the first genome that contains a K-mer for now. So as an example that how the observation we just saw work, so if we consider K-mer CAT, the first occurrence is in the genome at node 1, and the last occurrence is at genome at node number 5. So the smallest subtree that contains CAT will be returned as node number 2. And we know that there is another occurrence of CAT in node 3. So this is actually all 3 genomes that contain CAT, and again, 2 is a correct value. So actually, we already have a really small index that's really good at finding the first occurrence of a pattern in a text, which is Kreft and Navarro's LZ77 index. So we can reuse component data structures. So what if we build one LZ77 index for the phylogenetic tree and another one for the reverse of it? So also we know that random access to the phylogenetic tree gives us random access to the reverse of it. So then we would be able to find the roots of the smallest subtree whose genomes contain all the occurrences of the K-mer without us knowing K at the construction time, because we do not need to give LZ77 K, we just build it. So this will bring us to Katka, which is the Finnish word for shrimp. And as we can see, the shrimp size is way smaller than the sea monster that we saw at the first of the presentation. And surely we will find out why exactly Katka is smaller than a kraken. So we do not need the full power of LZ77 index. As a matter of fact, we don't want it to report all the occurrences. We just want its ability to say whether a pattern occurs in the index text or not. So I'm going to go through how LZ77 parse works. So what we're going to do first is that we're going to concatenate the genomes that we had in the previous tree, which were 5 genomes with a special character for which here is $. And then we're going to do the parsing. So in LZ77 parse, every phrase that is the result of a parse is either a character that we have never seen before, or it's the longest prefix of what's left that occurs in what we've seen before and is followed by another character. So I'm just going to show you through an example. For example, here, we're going to start with the first character, G. And since we haven't seen G before, we're going to parse as the first phrase. Then we continue to the next character, which is A, and it's going to be our next phrase. Since we have not seen A before, then we're going to the next character, which is T, and we have not seen character T before, so it's going to be, again, a new phrase. Then we continue to the next character, which is T. Since we have seen T before, we're going to proceed to its next character, which is A. And we have not seen TA before, so it's going to be the new phrase TA. And then we will continue this process until the end of the concatenation, until we get all these phrases. So Farag and Thorup, stock 95, they came with a lemma that the first occurrence of any substring touches a phrase boundary in the LZ77 parse of the concatenation, and the last occurrence of any substring touches the phrase boundary in the LZ77 parse of the reverse concatenation. So it's worth mentioning that they were not even looking for the indexing. They were actually studying on the pattern matching that they came up with this lemma. So I'm going to go through how LZ77 index is going to work here. So what we're going to do is that we're going to take our phrases, and we're going to have 2 columns, one that contains all the phrases except for the last phrase, which I'm going to say now in short. And we're going to have another column which for each phrase, we're going to write the following substring that is in front of it. So for example, for the first phrase G, we're going to have $ATTACAT till the end of the concatenation. And then for the next phrase A, we're going to have $TTACAT, which is the string that comes after it until the end of the concatenation. So for the one to the last phrase, we have only one phrase, GATTA, GATA, which is the last phrase which is remaining. So we're not going to include the last phrase in the phrases column because it's not being followed by any other strings. So that's where we end. And we need to note that the pattern that we would have does not include $sign in it. So we can get rid of all the characters that are at the left side of the $sign in the phrases, and the characters that are at the right side of the $sign in the strings that follow that phrase. So for example, here we're going to get rid of $sign A and the rest of it. Here we're going to get rid of $sign AG and the rest of it, and so forth for all the other suffixes. And then we're going to get rid of all the characters before the $sign and $sign itself for the phrases. So here we'll get rid of AT, and here we'll get rid of CAT, and here the same process will happen. So the phrases, and I'm going to refer to this column as phrase boundaries. The phrases and the phrase boundaries that we're left with are these. So what we're going to do is that, so what we're going to do is that we're going to build a grid, and we're going to put the phrases in the co-lexicographic order on top, and the phrase boundaries in the lexicographical order on the right hand. So we're going to fill the table with dots for which of the dot indicates that this phrase is going to be on the left hand of the phrase boundary that is on the right side of the dot. For example, here we had GATT and AGAT, so we're going to put a dot for the phrase and the phrase boundary. Also, another example here, we have TA and ATA, both having a dot for CAT, which means ATA and TA were followed by CAT. So if we look at here, yes, TA and ATA were followed by CAT. So the thing is that we noticed that we don't want LZ77 to report all the occurrences. So actually, we want the first genome that contains the occurrence of the pattern only. So what we're going to do is that we replace the dots with the genome nodes. And instead of using a range reporting data structure, we will use a 2D range minimum data structure so that given a query box, we can return the minimum value of it. So let's assume that we're given a Kmer GATA, and what we're going to do is that we're going to look at every way to split it in two phrase and a phrase boundary. So the first way to split this, before I go into this, we need to remember that we do not want an empty prefix. So we're going to first start with one character prefix, and then we'll split it from the rest of the Kmer. Then we're going to have 2 characters for the prefix, and then we split from the rest of the Kmer, and then 3 characters, and then all the characters and an empty suffix. So at each step, we're going to find the phrases that end with the first split. For example, here, we're going to find the phrases that end with G, and we're going to look at the phrase boundaries that start with ATA. So the intersection of the vertical slice here and the horizontal slice here, which contains the phrases that ended with G and the phrase boundary that started with ATA, will give us a box that contains 2 values, 5 and 3. So we said that we're going to use a 2-dimensional mean range query. So this box is going to return us the minimum value between the values we have, which is going to be 3. So next, we're going to do the same thing for the next split, which is GA and TA. So as we can see, we do not have any phrase that ends with GA. So we will not have any query box here, even though we have TA. We have one phrase boundary that starts with TA, but since we don't have any phrases here, we're not going to have a query box. So we'll proceed to the next split. We have GAT, the same thing happens here. We have phrase boundaries that start with A, but no phrase that ends with GAT. So we'll proceed to the next split, which is GATA and an empty suffix. So there's actually a phrase that ends with GATA. And we know that all suffixes are prefixed by the empty string. So we're going to include all of them. And we will have this long skinny box here, and the minimum value will be the only value we have here, which is 9. And then we're going to take the minimum value among all the boxes that we had so far. So the previous minimum value was 3, and here we have 9. So our minimum value overall is going to be 3. So that means that the first occurrence of the Kmer that we're given GATA is at node 3. And as we can see here, yes, the leftmost occurrence of GATA in a genome has happened in node 3. So if we put all of this together with appropriate component data structure analysis, we will get this following theorem, that for a phylogenetic tree whose genomes have total length of n, we can store the phylogenetic tree in O of z log n plus g divided by log n space, where z is the number of phrases in the LZ77 parse of the concatenation. And given a pattern of length m and integer k, we can find the root of the smallest subtree of T that contains all the genomes in which k-mer of the pattern occurs. And it will be in the total time of O of km log epsilon z. And if there are no two genomes in the tree that are identical, then our space bound will simplify to O of z log n. So as the new work, Ben Langmead's intern Mary Chang found that using maximal exact matches or MEMS, we can get better results than using k-mers. So that even includes the k-mers that are given at the construction time, at the query time. So that is, we should find the MEMS of the pattern with respect to the phylogenetic tree. And then for each of those MEMS, we should find the root of the smallest subtree that contains all the occurrences of the pattern in the tree. Also, Yun and Gao had a DCC paper about finding MEMS with the LZ77 index, and Gonzalo has an archive post about it as well. He also has a student that is implementing CADCA with MEMS as well, so I'd suggest you stay tuned with implementing CADCA with MEMS. So that's all I wanted to talk about today, and thank you for listening. Please let me know if you have any questions.
Thank you, Sana. There are no questions in the Q&A chat. Are there in the room? I have a question. How about running time? Did you analyze it? Or I don't know if you mentioned, maybe I missed it.
So what we have right now is the running time in theory. We have not yet run the experiments. This is a very new paper actually. And yeah, like we're going to evaluate the other ways of implementing CADCA first, and then we're going to do experiments, and hopefully we'll have the results about that.
Okay, thank you.
No
Thank
worries.
you. So there are no questions in the chat. I assume there are not
don't have
in
a
the room.
question.
Are there?
Nadia?
Yeah, go on.
I don't have a question because it was really interesting and I'm very overwhelmed. I have to think about it. I would just like to compliment you. I'm really impressed. I heard at the beginning that you're a master student, and yeah, I think maybe it's not easy to be Travis's master student, but you're doing really well. I mean, it's impressive. Yeah. So the talk was fantastic. Thank you very much.
Thank you so much. It warms my heart.
Oh, Gonzalo has a question.
Thanks, Juja. Okay, so
Gonzalo.
we should move on to the next speaker, I would say.
Wait. I have a question. You go too
Okay,
fast,
we're
Nadia.
a bit late. Go on. Just one question.
Okay, congratulations for the talk, and the work is quite interesting. As for implementation, I understand you haven't yet started. Is that correct?
Yes,
Okay.
we haven't done the experiments yet.
Okay, because I have a suggestion that maybe you don't need to store those numbers that you showed on the grid on the matrix, because they are genome numbers, but the index already stores their phrase numbers just in order to do the binary searches for the prefixes.
Right,
So
yes.
all you need is a bitmap that marks which phrases end a genome, and you can do the range minima directly in the phrase numbers, and then obtain the genome number from the bitmap. So you will save a good amount of space.
Right, yeah. That's actually a very good point. Thank you so much for mentioning that. We'll definitely remember it.
You're welcome.
Thank you.
Okay, let's move on. Next paper is computing all versus all MEMS in run length encoded collections of hi-fi reads. The authors are Diego Diaz, Simon Pugliese, and Lena Salmela, who is going to present the paper.
Me, Diego.
Yeah.
By the way.
Please, Diego. The
Can
stage
you
is
see me?
yours.
Okay. Thank you for the introduction. As you were saying, this is a joint work with Simon Pugliese and Lena Salmela that is there. We're all from the Department of Computer Science in the University of Helsinki.
I cannot see the slides. I don't know if it's a problem on my.
I can see the slides.
Okay.
Some
okay.
delay. Okay. Yes, now the pointer is working. Okay. Hi-Fi reads are a recent type of sequencing data from PacBio. PacBio is actually an important company in sequencing industry. In general, the main aspect of this kind of data is that they are longer than Illumina reads, which is actually the standard nowadays, I would say. Several thousand of symbols in length. They have low error probabilities, so in reality, the quality of this seems, I am seeing the Zoom now. Yes, they have low error probabilities, so they have good quality. The probability of an error, of a misprediction of the sequencing of the sequence of the DNA is actually quite low. In all these features actually are good for complex applications in genomics, as Lina were explaining in her talk. Now, there are some challenges, though. It's not working again, I guess. It's working. In general, it's expensive to compute optimal alignments or any kind of heuristic, because now the FM index, which is actually the gold standard for reads that are from Illumina, is not actually that good because the reads are long and we need to support more errors, right? So in that context, the FM index shouldn't be that fast. And the other important problem is that this kind of technology is prone to produce homopolymer errors. So when we are sequence the DNA, we may have that the runs of the same character are going to be mispredict. So for instance, this is the original DNA, and these are the hi-fi reads that we are going to produce with the technology, and we see here that there are some gaps. This is because the machine is actually mispredicting the length of these elements here. Now, in general, the state-of-the-art tools align hi-fi reads using these synth and extended heuristics, minimizers and collinear chaining, dynamic programming, on all the things that have been developed in that area, right? Now, but in general, one is interested in maximizing actually the number of seeds that we are able to compute in the problem, right? Because in general, the extension part in the heuristics is actually a bit slow or a bit expensive because we have to perform these dynamic programming methods. And here we are interested in computing alignments between all versus all reads because they are actually good for reference-free analysis. And as was mentioned before, an important way of reducing the number of seeds is actually computing these MEMS, right? So MEM, in simple terms, is actually an exact match that cannot be further extended to the left or the right because either we have mismatches or we end the end of one of the reads or the sequence in this case, in any kind of a string, or the combination of both situations, right? But the particular problem with hi-fi reads with this kind of ideas is that the homopolymer errors, the problems in the estimation of the runs, they truncate the MEMS, right? So the intuition here is that if we run length encode the hi-fi reads, then the manipulation of homopolymer errors shouldn't be that difficult in general. For instance, we have these reads here. They have these mispredictions. And in a general setting, we have to rely on dynamic programming actually to find these specific gaps. But in this case, if we have like the run length compression of these sequences here, now if we perform exact matches here, we don't have that much difficulty in finding the exact match. Now we have to deal with the length of the runs in order to actually validate the alignment that we are trying to actually compute. This seems to be a bit simpler than performing the dynamic programming here. Now, I will formally define this all versus all mem problem. Suppose that we have a string collection of k strings, in this case, the hi-fi reads with n total symbols, and the problem of all versus all mems consists in reporting every possible pair of substrings from different strings in the collection, such that they have a substring with a regular mem, and the length of this exact match is actually over some parameter tau that we define as an input, right? We're not interested in mems, for instance, between substrings within the same sequence. This is actually something that is driven for the specific problem of dealing with hi-fi reads. Now, run length encoded mem is actually not that different in definition, but we are now working with the run length encoded strings or hi-fi reads. So we have two strings, A and B, and they are encoded in run length encoding. And they are going to have a run length encoded mem if their symbol sequences, meaning these symbols here, the symbols that conform the runs, have a exact mem, and the corresponding length of the sequences, they don't have an excess that we are going to define soon, below some threshold E. This excess is actually a specific metric that we are going to define. So considering all these ideas, we present a framework to compute all versus all run length encode mems on a collection S, in a collection S of hi-fi reads. So in practice, we're going to work with R, which is actually the multiset that we obtain by storing the original reads on S plus their DNA reverse complements. This is actually quite common in sequencing in general, because in most of the cases, not always, we don't know actually the DNA strand from which the reads on S were produced, right? So we have to consider R anyway, especially, for instance, if we want to perform genome assembly or SNP calling or things like that, right? So we show how to operate over the BWT of R as an implicit bidirectional index. We will see why this is actually useful in this context. And we are going to adapt the algorithm of Belasogi and others that detects actually all versus all mems to our specific problem using actually this implicit bidirectional index that we are going to implement on top of R. That is the main idea. Now, as I explained, we introduce some specific metric specific to this kind of problems that we call excess, and actually we are going to use it to filter these approximate matches that we are going to obtain in this run length encoded setting. And then we propose an alternative solution to actually report the positions in the sequences for the mem that we're going to find in this all versus all mem that use a grid data structure. So this is a quick review how this algorithm works. In general, we actually visit the suffix tree node using the Wagner links. And for that, this paper actually produced a bidirectional BWT, which is actually a regular BWT with the actually that contains the reverse of the text, so we can simulate some suffix tree functionality. And the idea is that imagine that we're visiting the suffix tree nodes in the BWT, so we have a range that actually represent our suffix tree, the node. The node is actually represented with the pink box here, and this is its range, and these actually are the ranges for the children of the node. And we visit actually the suffix link associated to this specific node by performing some sort of backward search operation in the BWT. So we will receive, or we will produce another range here, A prime, G prime, which is actually a Wagner link for this when we follow C. But in this case, we are going to actually report, because if we see the symbols that are actually flanking our specific pattern that is labeling the node that we follow here, that we reach here, actually we have different symbols. And by definition, we should find here a mem. So what we are going to use is actually use the bidirectional functionality of the VWT to actually split this into the ranges for the children, and then we have to compute all versus all possible combinations. For instance, we have the elements here that are suffixes, and then we are going to report a mem between this sequence, for instance, and this sequence, right? Because, no, sorry, this sequence, G, no. Because both are flanked by different symbols. Notice that, for instance, here and here, we don't have a valid mem because both are preceded by the same character. So it's not actually a valid mem. So in general, this is quadratic on the size of the alphabet, right? Because we have different combinations of the symbols. Now, we can actually implement for free a bidirectional BWT on R because it's almost the same, but we're adding some sort of permutation on the symbols. And the only main difference is that we're not using two different BWTs, one for the reverse of the text and one for the direct sequence of the text, but just one, and we're combining all together in one BWT. But we need this anyway because we are dealing with hi-fi rates, right? So the idea is actually not that different from the bidirectional BWT, but we're including the DNA reverse complements. The main idea is that for each node in the suffix tree, we're going to have the same range as before, but now we have like an equivalent range that we have to maintain synchronized. This range actually keep the node that labels the reverse complement of the label for this node. In other words, for instance, this is actually the label for B, right? If we take the reverse complement, we have this sequence. Now, this is the representation without changing the symbol. Here, the underline represents actually that this is the reverse complement of A, this is the reverse complement of T, A, G, and so on. For clarity, I am not changing actually the symbol. So what we have here is TAT, CGT. And now, the symbols that we see here are in here, are actually the same because for each string on the set, we're actually including its reverse complement. So there is some sort of symmetry in the VWT. So when we perform a password search to get the winner link for this, we have to keep synchronized this other node here. This will give us a new range, right? But this is actually a compaction, or I mean, it's a sub-range of this range. This is actually the same idea as in the bidirectional VWT. Now, the thing is that we're going to exploit how this permutation actually is to compute this in one operation. For instance, let's say we want to follow C, right? The winner link level with C for B. Now, in order to obtain the new range, which is actually here, we need to count all these elements in the box. And for that, we need to compute the symbols that are lexicographically smaller than the reverse complement of C. So we have C, this is its reverse complement, DNA complement, not reverse complement, DNA complement, and these are smaller. But if you notice here that those that are smaller are actually greater than C here. So in practice, what we have to do is actually count the number of symbols that are greater than C in this range. Because there is symmetry, we found, for instance, that we have 3 elements here, so we have 3 elements here. And we can compute this with a range count, which is actually something common in the wavelet tree. I mean, this is a regular operation in the wavelet tree. That is actually the default representation from the BWT when working with this kind of analysis. Now, this is the same idea, but for the other nodes. So this actually will allow us to compute this break of the ranges into the different ranges for the children for V when working with the bidirectional BWT. So we define some metrics to align this run length and code strings using this idea as I explained you before. Basically, we have this equivalence between different strings. That means that if we have strings with a different sequence, but if we run length and code, and then the symbols of the runs are actually the same, this is actually equivalent. Then the excess is just simply, we have the run length encode of these equivalent nodes or equivalent sequences, and then we obtain the absolute value of the length. And then we take the maximum. This is actually the excess. And the intuition is that if we have an alignment of two sequences that are actually homopolymer errors, this excess should be small because the machine is actually bad at predicting the length, but it's not that bad. I mean, we don't see here a big difference in two runs that represent actually, or that fall in the same encoding, in the run length encoding. So packing everything together, the idea consists in first run length compressing R, and then we create a new collection, RH. And for doing so, we just scan the run length encoding of R, and we push symbols, or the symbols, into a new specific sequence, right? Or a new collection. Basically, if we see a symbol and we see that the length associated to the length of the run associated to that symbol is 1, we push the character as it is. But if the length is actually greater than 1, we put a meta character that is just marking that symbol in particular is representing a run. And we have a specific meta symbol for each DNA symbol. So we are just doubling the alphabet of the DNA. So we construct the BWT for the symbols of the runs, and then we have to reorder the lengths of the runs so we can use them during the analysis or during the computation of MEMS. So let's say we have a suffix in the collection RH, such that this is actually the J's suffix in lexicographical order. So if the symbol at the beginning of this suffix is actually a meta character representing a run, we put the length associated to that rank in a position that is actually associated to the suffix array position J. And then we run the algorithm of Belasogui and others to detect MEMS on this specific encoding and on top of the bidirectional BWT I just explained. And then we filter MEMS using this excess idea. So let's say this character here is actually a meta character representing a run. Then we are implementing we are running the algorithm of Belasogui, and eventually we reach this sub-range that we have to actually partition because we need to report the MEMS. So if we have to report this sequence versus this sequence to be a MEM, first we have to decompress their sequences by performing inverse LF mapping to compute actually the length associated to every meta character that we see. We can obtain actually the length associated to a specific meta character because we are reordering the lengths in suffix array order. So, and because we are using inverse LF mapping, we are actually computing that. And with that sequence, actually, we can compute the excess of this sequence and this sequence. And if the excess is actually below some threshold that we define, eventually we say, okay, we have here an run length encoded mem. And we have to do this every time we visit a suffix tree node, and eventually we complete the algorithm. The time complexity of computing a specific run length encode MEMS in a specific suffix tree is actually this. This is actually the alphabet of the new sequence that we obtain by doubling the alphabet of the DNA. And this actually accounts basically for computing this partition on a node in which we have to report MEMS. And this is actually the length of a range. For instance, the first term actually comes from the partition of this, and this is actually the length of this range. And this is quadratic because we have to compare all against all in the worst case, and we have to actually decompress the full sequence to actually check if they have access or not. And this is actually the length of the sequence. Now, we can do an alternative approach to actually report the position of the MEMS in the sequence or in the collection. And for that, we are going to construct a grid of n times n dimension in which we are going to put the suffix array values. We need them anyway because we have to compute the positions, right? So let's say the rows are actually the distinct suffixes, and the columns are actually the distinct suffixes too. So in every cell, in every row, we're going to put in the column associated to its LF mapping, the suffix array value, actually. For instance, if we follow this, we are going, for instance, like here. So instead of putting something here, we put it here, which is actually the projection of the rows. So we encode this in a succinct data structure, and we know that this is actually simpler to scan because we know that, for instance, this column here will not yield actually mems because all the elements are preceded by the same character. And this column here, this row here, is actually not producing a mem because all are followed by the same character. So they are somehow incompatible, right? We impose an order by using a grid. This actually applies to all grids. For instance, for this area, we have this, and this is incompatible. If for this area, we have this, and so on. So what we're going to do is actually obtain all the elements in this range, and then we're going to actually report mems with all the elements from the other areas of the grid that are compatible, right? So for instance, if we pick 60, we know that this area is not compatible because they are followed by the same character, but the others too. But the others are actually compatible. For instance, 60 and 2, and 60 and 12, and so on. So the further work is actually implementing all these ideas I just explained you. There are some that are already implemented, but not everything. We have to actually improve the approach to compute dexes between different sequences, right? Because it's actually a bit expensive so far in the current description of the method. And we want to extend these ideas to other datasets that are actually interesting, like proteins, because it's actually the alphabet is high, and the performing these alignments is actually a bit complex. And we also have these run length problems, and that's all.
Okay, thank you, Diego. We are late, actually. The slot is totally gone. So I see no questions in the chat. I have none. So I would move on, if there's no question from the room, to the next speaker, the last one of this session. Should be online. I don't know who is going to present. Is the speaker ready? The authors are Guillaume Fertin, Géraldine Jean, and Anthony Labarre. The title of the paper is Sorting Genomes by Prefix Double Cut and Joins. Is any of the authors connected?
Yes, I'm here.
Okay, hello, Géraldine.
I'm trying to share my screen.
Okay.
Here we are, I think.
Yes.
Yeah.
Cool. Yeah, you are on page 7.
Yes.
Okay. Okay, please, the stage is yours.
Thank you. So hi everybody, so I'm Géraldine Jean from Nantes University, and I'm glad to present the work I have done with Guillaume Fertin and Anthony Labarre. So the context of our study is about understanding evolution through genome rearrangements, and in this context, the genome can be seen as an order sequence of genes, and the genomes can evolve by rearrangements called genome rearrangements that are large-scale events that modify the gene order. So when we want to study evolution through genome rearrangement, we take as input 2 species, 2 genomes. Here, for instance, we have the genome of mouse and the genome of human. So you can see that the genome is a sequence of numbers, and each number is signed because we take into account the strand information. And what we want to infer is the minimum number of operations needed to transform one genome into the other, and it's called the distance. So this kind of programs is heavily studied since the 90s, and there exist many variants depending on the type of genome we consider. It leads to different genome models. So for instance, we can represent genomes by permutation or by strings, whether we consider gene duplication or not. And also signed version or unsigned version, whether we take into account the strand information, but also structures in graph like path and cycles. Also, we have to take into account different rearrangements. So one unique rearrangement or a combination of some of them. So here I put some example, the most famous ones. So inversion, transposition, or double cut and join. And what you can see here on the picture, so it's different example of operation. And so what we can see, it's each operation cuts at different places in the genome, and the number of cuts depends on the operation we apply. It leads to several blocks, and these blocks are then reorganized by passing their extremities in different way. And in the prefix constraint context, we add one constraint, which is one of these cuts has to be applied to the leftmost position in the genome. And while the unconstrained version is very well characterized, it's not the case with the prefix rearrangement problems. There is still a lot of things to do. And so our interest here is mostly theoretical, and we provide here an algorithmic study for sorting by signed prefix DCJ for unichromosomal and linear genomes. So first I will state the problems by showing how we consider here the genomes and by presenting the operation, the prefix DCJ, and then I will provide some algorithmic results. So here you have a genome G with 5 genes, 1, 4, 3 to 5. And the unsigned representation consists in, for each gene correspond to a vertex in my representation. And we add 2 additional vertices at the extremities, so here 0 and 6. And therefore, the unsigned genome can be seen as a collection of vertex disjoint path and cycles on the set 0, 1 to n plus 1. In the case we have a linear genome, then we have a single path with endpoints 0 and n plus 1, like the genome we provide here as example. And another important genome is the identity genome, which is represented by a single path 0, 1, 2 to n plus 1. In the signed version, we have to take into account the orientation of each gene, and to do so, each gene will correspond to 2 vertices in our representation. So we take the absolute value of the gene that we multiply by 2, and so the vertices are 2 times the absolute value of the gene and 2 times plus 1. So for instance, minus 1 give the vertices 2 and 1, and the order of these 2 vertices are given by the sign of the gene. In the same way, we add at the extremities 2 additional vertices, so here 0 and 11. So it gives, for a signed genome, as a representation, a perfect matching over the set 0 to 2n plus 1. The identity genome in this context is a perfect matching the sets 2i and 2i plus 1 for I from 0 to n. So that's it for the representation of the genomes. Now for the operation is the prefix DCJ, so double captain join. So first I will present the classical operation, classical DCJ operation applied. So here on the signed genome, it consists in 2 steps. The first steps consist in deleting, so cutting 2 ages, so here AB and CD, and replacing them by adding either edges AC and BD or edges AD and BC. So here's the case I on the example. We replace AB and CD by AD and BC. And in the prefix version, we add an additional constraint. That is that one of the 2 edges has to be the leftmost edge in the genome. It means that 0 must belong to E or to F. So with the same example here, I just move the edge AB at the first position. So I cut AB and CD and replace those 2 edges by AC and BD. So now we have the genomes and the operation. I can introduce the 2 following problems, 2 decision problems. So sorting by sign prefix DCJ or SSPDCJ take as input a sign linear genome G and a number K, an integer K. And the question is there a sequence of at most K prefix DCJ that transforms G into the identity sign linear genome? We have exactly the same problem, but with the unsigned version. And so the goal here is to provide an algorithmic study for both problems. Just a remark to understand what follows. We note by PSDCJ and PDCG the prefix DCJ distance of a signed or unsigned genome G, respectively. To understand the algorithmic results, first I have to introduce the breakpoint graph on which the results are based. So first, the breakpoint graph for a signed genome G. So it just the breakpoint graph is just the union of the signed genome G and the signed identity genome ID. So here the genome G is represented with black edges and the signed identity genome ID with the dash edges. And so the union of both genomes give the breakpoint graph here below. This graph can be uniquely decomposed into C alternating cycles. So here we have 3 cycles, So the first one here in bold, the big one. And we have 2 more additional cycles, so this little one with 2 edges, and the last one. We can go a bit further with studying the type of cycles according to their lengths. So length of a cycle is the number of black edges, and we call a trivial cycle a cycle of length 1. So C1 here represents the number of trivial cycles, and on the example we have 2 trivial cycles here in bold, so this one and this one. So the goal here is to transform this breakpoint graph into n+1 trivial cycles, because what we want is to transform G into the identity, and so the black edges have to correspond to the dash edges at the end. We can do exactly the same thing with the unsigned version. So here an example with the genome G and the identity. So we get UBG as a breakpoint graph, but unsigned. The difference is that the decomposition of this graph is not unique. And what we need, it's an optimal decomposition, optimal in the sense that it has to minimize C minus C1, so the number of cycles minus the number of trivial cycles. And we are lucky because there exists an algorithm in P to compute such an optimal decomposition in order to obtain C star and C1 star. So here, the decomposition we obtain, the optimal decomposition, is composed of 3 cycles and 2 trivial cycles. So the red one with the 2 trivial cycles for 3 and the 2 little one for 2. So again, the goal here is to transform this graph into n+1 trivial cycle. So the first result I want to show, it's a new lower bound for the sorting by sign prefix DCG. In the case of the sign version. So you have to know that each DCJ, but also prefix DCJ, acts on at most 2 cycles of the breakpoint graph. And this operation have the same effects than exchanges on the cycles of a permutation. So we can use the lower bound for prefix exchange distance and apply it on our problem. So it gives this formula: the distance is greater or equal n+1 the number of trivial cycles we want to reach, C the number of cycles we have, minus 2 times the number of trivial cycles, plus minus an additional component here, depending if the genome starts by element 1 or not. So on the example, the distance here is greater or equal to 3. And we can do exactly the same thing with the unsigned version, but here using the optimal decomposition of the unsigned breakpoint graph. And we have exactly the same lower bound for this example, so greater or equal to 3. Thanks to this new lower bound, we are able to prove that the sign version of the problem is polynomial time solvable by showing that the lower bound is tight. So we showed that by an exhaustive study, looking at all cases possible. So we look at the first element. So either the first element here, x is equal or not to 1. So in the case x is different to 1, we look at the element x prime. So x prime is equal to x plus 1 or x minus 1. That's why there is dash edges here. And we will apply the DCJ on the first, of course, the first edge here and the other edge with x prime. And the result depends on the value of y here. So y can be equal to 1 or not. In the case y is different to 1, we look at the difference in terms of cycles. So we split here one cycle, so we will gain a new cycle. So delta C here denotes the difference between the number of cycles we have and the number of cycles we had before. So we gain one cycle, and the cycles we gain, it's a trivial cycle. So we have one more trivial cycle. And delta plus here represents the difference between the additional component here. So before x was different to 1, so we were in 2 cases here. And y again is different to 1, so we didn't lose anything. Yeah, okay, Nadia. When y equal to 1, we gain not only one trivial cycle, but 2 trivial cycles. But because y is equal to 1, here we have like a penalty of 0, so -2. But when we look at the total difference, it's -1. And the last case is when the first element x equals 1. In this case, we look at the first edge where the absolute difference between y and z in different of 1, and we cut here. It leads to, so here we will merge 2 cycles into 1, so we will lose 1 cycle, and the cycle we lose is a trivial cycle. But instead, the genome will start by something different from 1. So we'll gain here 2. So in total, we have -1. So, and in any case, here, we will decrease the value of the lower bound. And so we show that our lower bound is tight, and we have a polynomial time algorithm for solving the sign problem. For the unsigned version, the complexity remains open, but we conjecture that it's NP complete. And we provide 2 algorithms, but this time based on the number of breakpoints. So quickly, the number of what is a breakpoint in an unsigned genome? So an age UV is a breakpoint if 0 does not belong to this age, and either the absolute difference between U and V is different from 1, or E has multiplicity equal to 2. So here we have 3 breakpoints in this genome, 3, 6, 1, 2 because there is multiplicity 2, and the loop on 5. And so the 2 algorithms we provide, so the first one is an approximation algorithm with a ratio 3/2, so lower than 2. So I won't go into details. If you have questions later, I can reply. And the other one is a FPT, so fixed parameter tractable algorithm with respect to parameter number of breakpoints. So again, I won't show the detail, but it relies on a bounded search tree. And what we can see is that the complexity, the exponential part, is only depends only on the number of breakpoints, so B. So to conclude, this work is the first algorithmic study for sorting by signed or unsigned prefix DCJ on unique chromosomal and linear genomes. We have provided new structural lower bounds based on the breakpoint graph, And because prefix DCJ generalize prefix reversals, it's also a new lower bound for sorting by unsigned prefix reversal. We have shown that the signed version of the problems is polynomial, while the unsigned version, the complexity of the unsigned version is still unknown, and provide two algorithms. And so the open question for this work is, of course, to characterize the complexity of the unsigned version, but also try to improve the ratio of the approximation algorithm by making good use of the new lower bound, and to extend this work to more general genomes, because here we restrict the study to linear and unichromosomal genomes. Thank you very much for your attention, and if you have any questions.
Thank you, Geraldine. We are actually very late now. I don't know if there's questions from the room. I would say at most one. There's no question in the chat.
No question.
Okay, so is there any question from the room?
No questions.
Okay, that's better for the schedule. So I close the session, thanking all the speakers, and
thank you, Nadia.
see you with the next session, which will be in the Chilean afternoon, and before that there's the tutorial on graph database. I don't know if there's some announcement from the organizers.
Yeah, thank you, Nadia.
Geraldine, you are still sharing the screen?
Okay, thank you. Any questions?
Okay, good. Good. We can start now. Next, we have a tutorial by Aidan Hogan about graph databases. This might be a new topic for many of you, probably, but we think it will be a good contribution for the conference. So thank you, Aidan, for the tutorial.
Okay. Thank you, Diego, for the introduction. So we have a tutorial of 3 hours on a topic that might be new to some of you, graph databases. First of all, thanks to the organizers for the invitation to give this tutorial. So in this first part, it will be a tutorial split with Tomogoy. Tomogoy, if you want to say hello. So we're going to give the tutorial in different parts. So today, I'm going to give an introduction because it's a new topic to many of you and try to give you a bit of a setting for what's to come. What we'll end up with is various algorithms for evaluating queries over graph databases efficiently. And actually, some of this will tie in with what's working, what you're doing in your area, right? So we need methods for compact data structures. We need efficient algorithms for evaluations. And I already saw a lot of talks about graphs today, so there's already some intersection, it seems, right? So without further ado, there's a lot of hype around graphs these days. If you think of a database, you probably think of a relational database like tables or SQL or Postgres or something like this. But there's a lot of interest these days in representing data and querying data as graphs. So this has been around for a while, this concept, but it has a lot of momentum due to this concept called knowledge graphs. So in 2012, Google announced that they were releasing this knowledge graph. And this led to a variety of companies like LinkedIn and Microsoft and eBay and Uber and Airbnb and so forth, Amazon announcing their knowledge graphs, right? So this created a new interest around how to manage these graphs, how to do queries, how to do machine learning over them, and so forth. So in general, what are the applications? Where would you see these knowledge graphs appearing? Have you used any applications that involve knowledge graphs? If you use Google, you'll see on the top right panel, they have this, what's called a knowledge panel. Yeah, so it gives some information about the entity you're searching for. This is based on a knowledge graph. If you use any of these sorts of Siri or Alexa services, often the sorts of, if you ask a question, for example, a lot of the answers will be based on, not all of them, but some of them will be based on data from knowledge graphs. Airbnb is using it for recommendations, for events and so forth. Amazon Prime, Amazon has its knowledge graph for product recommendations and so forth. Uber Eats, based on different categories of food and creating recommendations and so forth. So there's a variety of applications, and probably you're using end applications that in some way involve a knowledge graph at some point now. So what is a concrete example of a knowledge graph? Well, a lot of the knowledge graphs we spoke about are closed, unfortunately. They're within companies, so we don't have access to them. However, there's a few examples of interesting knowledge graphs that we can see that are publicly available for use. So one I like, one that I talk a lot about, and sorry for the people who've already seen this this part, but or have heard me ramble on about Wikidata before, but I like Wikidata a lot. It's a project which is essentially like Wikipedia, but the idea is that users will edit graph data, and this will form a knowledge graph. So what do we talk about when we mean a graph? We talk about a graph where nodes represent entities, real world entities, and edges represent binary relations between those entities. So what kinds of entities do we have on Wikidata? We have, for example, University of Concepcion, which we have, where we have links instance of to this other entity, which represents a type called private university. We see a logo and so forth. We have an entity for Sharknado, one of my favorite movies. We see links to the type of movie it is, television movie, the part of the series, and this goes on. I can't show all the data available. I'm in there. So we also have galaxies, this ESO 137001. We have recipes like a toast sandwich where you put a slice of toast in between 2 slices of bread and you eat that. Sounds delicious. And so forth, right? So I mentioned that it's a graph. So how is it a graph? Essentially, if we think about how these entities are connected through these properties, we can see that it forms a directed edge label graph, right? So I've included you in the example. I was looking for some local examples here. So we see that essentially from University of Concepcion, we'll have links that are labeled to different entities in Wikidata, right? So this is essentially a directed edge label graph, right? So where is Wikidata used? Briefly, we know that it's used in various applications. One of the big applications we know about is Siri. So Siri in general, they won't reveal information about what sources they use, but somebody on Wikidata, because any user can go there and edit Wikidata, they added a date of death for Stan Lee before he had died. And then Siri at the same time started announcing to everyone that Stan Lee had died. So from that, we have a fair idea that Wikidata uses Siri in a sort of unfortunate way, but yeah. Okay, so there's a variety of applications for Wikidata. Why graphs? Why not tables? Why not trees? Why not something else, right? So in general, if we think about managing data, often we'll think about using a relational database. This is the typical standard kind of way of representing data, where we have nice, neat rectangular forms of data where we have everything organized. Relational databases are great. I'm not here to say that there's a problem with relational. Well, I am here to say that there is a problem in some cases with relational databases, but for many applications, a relational database works fantastically well. What is a relational database? We have some tables like debit, credit, account, exchange, client. We have some primary keys where we say that the values here are unique for the table. And we can do queries over these tables in something like SQL or in a more theoretical language, or something like the relational algebra, for example, and get back the results we want. So in the case of banks, this works really well because we know what we want to describe. And we can define a schema, what tables we're going to have, where we can describe precisely, more or less, the structure of the data, right? But in many applications, it's not easy to define beforehand the structure, right? So let's say, for example, we wanted to form some data about planets. We could do this in a relational database. We don't know initially what we're going to describe. We just know that we need data about planets, okay? So we can at least add the names of the planets, Mercury, Venus, Earth, Mars, and so forth. And then maybe we can continue adding more information with the new attributes or columns. For example, the distance, normalized by the distance from the Earth to the sun. We can add information about radius and gravity and the length of the days and the years and the temperatures and rain and so forth. And we have a nice table, right? So this is all well and good. What if we wanted to add information about moons? If we wanted to add information about moons, okay. So we decided, let's integrate some data about moons. We could add it here, and this represents a null, meaning that there is no moon. And in some cases, we have multiple values. Is this a good design? Do you remember your database course? No, this is what's called 0NF, right? Zero normal form. So what do? A new table. Yeah, so okay, we separate out the moon, we put a new table, we put the name, this is the primary key, that's why it's underlined, so that's the name is unique. And we have the planets associated with the moons. And let's say we add some more information. Now we have the discoverer and the year. But hey, okay, now we have for the Earth, we have Luna, Terra, and Null. So who's the discoverer of the moon, our moon? Be anyone? Okay, so we think, okay, maybe we'll leave that as a null, but that's not, nulls are not great. So we can maybe actually separate this. Maybe there's more than one discoverer in some cases. So we say, okay, well, actually we'll have a separate table for moon discoverer, which will give us a 0 to many multiplicity. And then we'll do discovery year like this, and all of these are names of moons, and so forth. So now we have a problem that you may have noticed. And the problem is that here we say Terra for some reason instead of Earth. Why do we do that? I don't know, right? But this is inconsistent, right? these planets, we would expect all of these planets to point to this table here. So what do we do in databases to avoid this sort of situation? Do you remember what it's called? It's called a foreign key. Yeah. So we say that this somehow, this column here refers to the primary key of the planet table. Yeah. So we add a foreign key, and essentially, okay, that forces us to fix this. We'll detect a problem here and say, hey, this doesn't appear, this Terra thing. Yep.
You said earlier that null was where it was empty, but some memories it was null to be used to say we don't know.
Yep.
And empty and I don't know is different.
It's a very famous problem with databases, that nulls are not used with the consistent semantics. That sometimes it's like not applicable. It exists, but we don't want to give the value. And that creates all sorts of problems with the negation. It gets really messy. So it's a really good point. Yeah, that's no. So in general, the good practice is to avoid nulls as much as possible. Yeah. Yep. Okay, so we have a problem. You may have noticed Pluto is in the table. Nobody complained, strangely. Often people get offended if I leave Pluto as a planet. So Pluto is no longer a planet. So what are we going to do? What would you suggest? Delete Pluto? Oh, should we lose all the data, forget about Pluto, that it ever existed? We could maybe keep the data, put it in a new table, dwarf planet or planetoid or something like that, right? All good? No, there's a problem. So this means a foreign key. So this means that this has to refer to planet name. So what do we do now? We have a problem with Pluto here. So, okay, we could remove our foreign key and just forget about that and say, okay, we didn't mean it in the first place. Sorry. And then, okay, let's say we continue. Now we start thinking about exoplanets, which are planets around other stars. At this stage, we'll probably get pretty frustrated and just give up with the relational database. Throw away the tables. If we compare this with a graph, what happens with the graph? We start with a node, represents Earth, for example. We start simple. We can add new nodes. We can connect those nodes. We can add labels to the edges to indicate the type of relation that is there. And life is free and easy, right? We just continue adding nodes, edges, and so forth. So here we say that Pluto is a planet, but now we know that Pluto is no longer a planet. What do we do in the graph? Just remove the edge. We can add a new edge, maybe to represent that it's now a dwarf planet instead. Not so difficult. If there's exoplanets, if there's need to model galaxies, yeah, we just add the galaxies, no problem. Yeah. So you can see that if we don't really know what we want to describe at the start, this graph representation is somehow much more convenient. Yeah. We don't need to go changing the schema every time to represent the graph. Okay. And so forth. So definitely it's not the case that graph databases are always what you should use. There's definitely pros and cons with respect to relational databases and graph databases. In terms of relational databases, the problem that we saw in this scenario is that we have to impose a schema or a structure from the start, which is the structure of the tables, the relational schema. What tables there are, what columns there are, what are the keys we use. Whereas in the case of the benefit of relational databases is that we have a structure imposed from the start. So it makes it easier to query and to optimize and so forth because our data follow a more fixed structure. So it's somehow more authoritarian in the sense that we have this graph or this relational schema that tells you exactly what kinds of data you can have, what data types and so forth that you need to follow. And if you don't want to follow them, you have to change the schema. On the other hand, the pros of graph databases, we don't have to impose a structure or a schema from the start at the level of a relational schema. The con is that we don't have a structure imposed from the start, right? So it's a sort of a trade-off. If you think your data are going to be more or less fixed, the schema, the conceptual idea of what you're going to store is going to be fixed, a relational database is pretty good. If you're unsure, a graph database is more flexible, right? So essentially, we don't have this fixed structure anymore, but somehow we'll have an organic structure if people follow the same, use the same labels on edges and so forth, and more organic sort of data structure will form. Okay, so we can see this on Wikidata. Hopefully you should be able to see my screen. Yeah, it's a little bit awkward for me because I've got the Zoom thing in the way. Let's see. Hold the mic like this, talk like this. Let's see. So that's okay. I think it's okay. So this is Wikidata. I'm aware that we're kind of short in time, so I'm not going to spend too long. But so here we see University of Concepcion. We see the stuff that I had screenshotted before. We see that we can follow links. And in this way, we form a graph. We can also add or edit data. So in the case of Cecilia, I think you're also educated at, you did your master's, I did some previous research at the University of Washington. Yeah, University of Washington. I've got two eyes. Oh. Yeah, and we've added a new fact to Wikidata. Okay. So just like this, we can add new data to our graphs, right? So how do we manage graphs? Any questions or doubts? You can interrupt me if you have any questions or doubts anytime. Okay. How do we query graphs? How do we manage them? Where do we store them? How do we index them? What structures do we use? That's the topic mainly of the tutorial. So we use graph databases, and graph databases have been growing in popularity. This is a Google Trends, which gets into some popularity of how many people are searching for things over time. Right? Just to give an idea, we see it's kind of going up, although maybe slightly down and then up again. Some systems, has anyone here heard of any of these systems? We have Neo4j, OrientDB, dgraph, BlazeGraph, AllegroGraph, Amazon Neptune, maybe, maybe not. If you haven't, you're in the right place. We'll talk a little bit about that. So we have a separation here where there's sort of two different communities. One is for property graphs, one sort of data model for graphs, and the other one is for RDF and Sparkle, more from the semantic web, which is my own area. So in terms of popular graph databases, there's this list of popular databases online here where they look at the number of questions and Stack Overflow and searches and so forth. And we see that actually they're still pretty niche. The first one is Neo4j, is the most popular at number 20. And we see here the list of some of the most popular graph database engines for Duos or AngoDB, OrientDB, and so forth. So they're still relative to relational databases. They're not taking over by any means yet, but as I mentioned before, there's increasing interest in this, this area. So getting into a little bit more of the technical details, we have two competing data models for graphs. We have what I called before a directed edge label graph, or RDF, which is like this. We have nodes, we have directed edges, and we have labels on edges that represent the type of relation that exists between the linked entities. Here we have a graph that's describing some star, TRAPPIST-1, and its planets, TRAPPIST-1b and TRAPPIST-1c, which are exoplanets. So these were discovered in Chile in the north. Okay. We have a second data model, which is a little bit more intricate, which is called the property graph model. And the property graph model, we have nodes again, but we have somehow labels. We can add labels to nodes to say what kind of node they are. We can also add, as before, labels to edges, but we can also add property value pairs to edges, and we can add property value pairs to nodes. Yeah? So in practice, some people consider this to be convenient, to be a useful feature, but we can also represent all of the same information. It's not that it allows us to add or express anything more, right? We can also represent this in a similar way using a directed edge label graph. It's just we have more edges, yep. More simple edges. So these two models are competing in practice, but I'm going to prefer the simpler model for today. Yeah, we'll see a little bit of the other model later when Domoga is talking. Okay, so that's essentially the data structure or the model we have. What about the queries? What kinds of queries can we do? So we're going to be looking at queries which are essentially graph patterns. Yeah. What are graph patterns? So we have different types of graph patterns. The first type is the basic graph pattern, right? So let's say, for example, over this graph, we wanted to find pairs of exoplanets orbiting the same star in Aquarius. Okay, so we have a star here, or sorry, a planet here and a planet here. They're orbiting the same star, and we see that the star is in Aquarius, right? So how would we write this? We could write it like this way, right? So we can write this as a basic graph pattern, which is just the exact same as a graph, with one exception. We can replace constants with variables, which I'm going to use this question mark to identify. Yeah. So it's the exact same structure. We build our graph pattern like a graph, and then we replace the things that we want to find with variables. Yeah. So what are we doing here? I mean, in terms of graph theory, it's essentially a homomorphism. Yeah, we're computing a homomorphism from this graph here to this graph here, where it should be the identity on all of the constants, and we can send the variables to whatever we want. Yeah. So what would the answers be? The answers in this case, we'd have star, TRAPPIST-1, 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 TRAPPIST-1b, 1b, 1c, 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 1b, 1b, 1c. Yeah. Does that make sense? Yep. Okay. I was going to mention something there. What was I going to mention? Yep.
So you want to say that, I guess you want to say that you shouldn't have 1B and 1B. Planet 1 and planet 2 should be different.
So you're surprised, right, by this result and this result here. Yeah. So you can add a filter, like the query languages will allow you to say planet 2 should not be equal to planet 1. But it's a good setup for my next slide, because other people have argued that really the semantics you want is more based on isomorphism or subgraph isomorphism, where you want a one-to-one mapping. In this case, you get the 1B, 1C, 1C, 1B. So I'm a fan of homomorphism and specify what you want to filter, kind of as an additional thing. But some people argue for an isomorphic subgraph isomorphism semantics. Yep.
If on the edge, or on the label of the edge,
yeah,
you have some relationship. For instance, being a moon of a planet is similar to being a planet of a sun. So those two relations are part of rotating around.
Yeah.
You would do it with the exactly same graph structure, or you would have to add some or it would be a self-graph model.
So that's also a big issue of debate for this sort of application. So it's essentially, what if you have sub-relations, right? So, or you have maybe an inverse, like for example, I think there's child and parent, which are inverses of each other. You can get one from the other. So there are various ways to tackle that. And there's a lot of work done in the semantic web in terms of ontologies that can take this information and apply automated reasoning. Like they could take a query which is just for child and expand it to look the other way for parent as well, for example. Or the other option is you write in your query somehow the different ways that your data could be expressed. The latter is obviously costly to the person who writes the query, but there are automated ways to rewrite queries to expand them to capture the related ways it could be expressed. Yeah. In terms of the graph, actually, there is one trick with, there's some details I'm not going into for time, but you can also describe the edge labels in RDF, so are in a directed edge label graph. So you could say, for example, that parent is a subproperty of child. You can represent that as part of the graph. And then you can give special meaning or semantics to the subproperty or subrelation edge. Yeah. So you can represent all that as a graph and then have some other layer that interprets that. More questions? Okay. So what's next? After basic graph patterns, we have what are called navigational graph patterns. So we have basic graph patterns plus regular path queries. What are regular path queries? Effectively, they're regular expressions over edge labels. So what does this mean? We'll give an example. Here we have something that looks like a basic graph pattern, but this isn't a simple label. It's a regular expression over labels. So this is instance concatenation, subclass 0 or many, clean star. Yep. So what this says is, from this variable, we want to go one hop of instance and then 0 or many subclass to reach the dwarf star node. What does this do in practice? We see here TRAPPIST-1 is not directly an instance of dwarf star. And this maybe goes a bit into Jeremy's question as well, that if we had semantics, we could figure out it is. but in this case we don't. So TRAPPIST-1 is not directly an instance of dwarf star, but it's an instance of a red dwarf and an ultra-cool dwarf, which are subclasses of dwarf star. They're special types of dwarf star. So what this query will do is go one instance and then zero or many subclass to reach the target type. Yeah, so effectively we're doing a sort of class hierarchy reasoning here. Not just for this, we can use whatever regular expressions we want on edge labels for whatever purpose we might like. Okay, so we get TRAPPIST-1 as an answer here. Find astronomic bodies and their constellation. In this case, we have to traverse some different parts here. So we can, for example, express with this query that we want to find something that's an instance followed by zero many subclasses of astronomic body, similar to this previous example we saw. And we want to do a join, right? So we want to, as well, make sure that this body has zero or many parents followed by constellation in a particular constellation. So what's the second part doing here? So the first part is making sure that somehow we travel all these paths here to get to astronomic body, right? So we can go one instance and then zero or many subclass to get there. And on the other hand, we want to check that it either has a constellation directly or it has a parent that has that constellation. Yeah? Make sense? So we're doing a join this time. So we're sort of combining these regular path queries with a basic graph pattern. And here's the answer. We get TRAPPIST-1, TRAPPIST-1b, and TRAPPIST-1c. That satisfy both parts. Yep.
I cannot help but notice that even though you mentioned the primary tables,
yeah,
you use table to give your results, but you could use a graph.
Yeah, it's also a really good point that we'll come back to that as well. There are other ways of doing it, but actually people really like the most popular. There are options in the query languages, and you can return graphs, but users most like tables to be returned. I think it's more difficult to represent a graph somehow. It's if you draw it or do you visualize it, or yeah, or it's also maybe custom. People are just used to getting tables as results. Yeah. Okay, questions, doubts? We're going to briefly recap the relational algebra from if you took a database course. I'm going to try to do it in 2 minutes. Relational algebra, because it's going to become important, was proposed by Cod in 1970, I think, in 1969, something like that. What does it do? It essentially defines the core of almost all relational databases in 5 or 6 operators. Yeah. The first here, the 5 operators. There's another syntactic one, which is to rename attributes, which I'm not going to get into. Join. Do you all remember what a join is? If I were to ask you how many results we'll get from the natural join between OR1 and OR2, what does natural join mean? Where the attributes they have in common, which is x, are equal. X OR1 equals x OR2. So we'll have HA, ABC, so that's 1. There's no more A's. IE, FG, that's 1, so that's 2. Hey, JK, there's none, right? So what we're doing is we're extending, with this join, we're extending the tuples from OR1, the rows of OR1, with the rows from OR2, such that the attributes they share in common are the same. This is a natural join. We haven't specified any selection criteria which we can do, but so here's the result. So we extend essentially HA. We look for the A's in OR1, and then we extend it with whatever results we find. Yeah. Selection, basically from OR, we can select all of the tuples, all of the rows, such that Y is equal to B. So how many results will we get? 2. Yeah. Projection. This time we're not selecting rows, we're selecting columns, we're selecting attributes. So we say, I don't care about Y, get rid of Y. That's what it gives us. Yep. So we're going in the other direction, union. Union gives us essentially all the tuples in both relations. Yep. So we get here probably 5 if there's no duplicates. There is a duplicate, EFG. Relations are defined in this algebra as sets of tuples, so we get 4. And finally, difference. You could probably guess where this is going. Gives you all of the tuples that are in OR1, but not in OR2. Yep. So in this case, it would be 2. We get rid of EFG because EFG is in OR 2. Yeah, so that's the relational algebra. There's other syntactic features and so forth, but this is essentially the core of relational databases. So what happens, and this seems too simple, but the idea is that you can compose these to transform relations into arbitrary other relations, which are your results table, effectively. Yeah. So yeah, so you can build more and more complex queries. And this is at the core of millions of relational databases that we use perhaps indirectly every day. So Jeremy pointed out that we have tables as results. So what about the idea of using the relational algebra over those tables? And this gives rise to complex graph patterns, or sometimes called relational graph patterns. And the idea is we just take our graph patterns like we saw before, and we add the relational algebra, and now we have all this sort of stuff you can do in SQL as well. So finding pairs of exoplanets orbiting the same star in Aquarius. Here, we saw this example before, but maybe we don't care about the star, right? The question doesn't say star, it says exoplanets, but we need a variable to check that, right? So we can use projection to say, just give me the planet 1 and planet 2. And what this does is, since the result of the basic graph pattern is a table, it just applies a projection over the table and gives you back the planets. Yep. What about instances of dwarf stars? So we mentioned before, we can do it with an RPQ as well, but with a regular path query. But if we want to find instances of dwarf star, well, we are interested in instances of dwarf star, as well as instances of red dwarf, as well as instances of ultra cool dwarf. So we can take a union and take the union of the results for those basic graph patterns. And that will give us a new relation. This would be under bags semantics, where we allow duplicates. Some query languages prefer set semantics, yeah, where we have no duplicates. We remove, or the duplicate doesn't matter. Doesn't change the results. Okay. So what about the idea then of combining the three things, right? Graph patterns, relational algebra, and relational path queries. So this gives us complex or relational navigational graph patterns, yeah? And you can do that. Yeah, as we saw as well, the navigational graph patterns are giving us tables. So we can combine all of them, yeah? So and a couple of examples for that, find on star astronomic bodies and their constellation. So here we saw this previously. So we were finding astronomic bodies, but now we want to remove the ones that are stars. We're not interested in stars, yeah? So how does this work? We use difference from the results that provide us with stars, yeah? So we have this second query here, which returns us the stars, which we remove using relational difference from the results. And here are the results we get back. So here we're combining RPQs, basic graph patterns, and the relational algebra. Yep. A couple of examples, just to have a quick look. I've already pre-baked them. They're already good to go, so to save time. A simple enough query to start with. We just have one relation. Wikidata uses IDs that are numeric because it doesn't want to give preference to a language. So it doesn't want to define the IDs in any language, right? So what are we looking for? If we hover over this is a language called Sparkle, concrete syntax. It's for RDF, or for directed edge label graphs. We're looking for employees of the Universidad de Concepción. We get a list here. I didn't add the names. I could add the names. Might have been easier, but okay. We can open up a couple of examples and see. Carlos Keller, Mario Héctor Ricardi Salinas, Roberto Donoso Barros. Okay, maybe not so interesting, but we can do something a little bit more interesting. We can query for the universities that are most common. The universities where people who work at Concepcion studied previously, which are the most common ones. Anyone want to guess what the first one would be? So no. Second? Okay, we'll go with Chile. Yeah, second is Chile. Third? Católica, yeah. And then we go. So these results are incomplete, obviously. That doesn't have a record of all the employees, but the idea is that users can complete the data that they want to. I should have added labels, but that's okay. We get an idea. Universidad de Havana, I think, has 3 people listed. This last query, just to give an idea of something maybe a little bit more visual. You can also visualize the results as something. This is a timeline of the inception of Chilean universities. I'd actually never heard of the Universidad Pontificia de Santo Tomás de Aquino. Don't you know anything about that? Apparently it's the first university in Chile. Or maybe it's just noise. Maybe it's just some user made a mistake or something. That also happens in Wikidata. Real Universidad de San Felipe, Catholic University of Chile. Let's see if I can scroll down. Here's University of Chile, and so forth. Yeah. So we can do queries over this graph, combining all the different nodes and edges and so forth. Okay. So I think we started at 12:20, right? Yeah, so I'll try. Is it okay if I try for 1:20? I know people are getting maybe hungry as well, but yeah? Okay. So how do we evaluate these queries? We have a couple of novels, a couple of books here. We have Slaughterhouse 5, The Good Soldier Schweik, and Catch-22. Anyone know what these books have in common? These books solve the hard problem for me, which is to find a concrete example that we're going to see. So any ideas? Something? So these are all anti-war novels. They're all about against war. And there's one other particular thing about them, which is that they're not just anti-war novels, but the authors themselves fought in the war. So they solved this difficult problem because I was looking for a concrete example to create this shape. So what is this? This is a query for these sorts of books, where we have a book whose writer is some author. That author fought in some conflict, some war, and the conflict inspired the book. Yeah. So it's a triangle. Yeah. And it's a nice example for what we're about to see. So we can kind of view, I've talked about tables versus graphs, but in some sense, they're different views. You can also view data as a table or as a graph. You can view a graph as a table as a graph. In terms of viewing graphs as tables or relations, we can just have a table, G, with 3 attributes, SPO. This is for subject, predicate, and object. The subject refers to the source of an edge. For example, here, SH5, writer, Vonnegut. Yeah. So we see that this table here represents precisely this graph here. Yeah. So we can have a table, and sometimes I'll use tables and sometimes I'll use graphs, but we're kind of referring to the same thing, right? So here we have a table where we have a bit more information about other similar books. We can also view a graph in this way as multiple relations. We could create, instead of having one relation G, we could think about decomposing each of the predicates we have here, or the relations, into binary relations as tables. Yeah. So we have writer, fought, and inspired. And this is sort of equivalent to a certain extent. There are some problems. It's difficult to return the names of tables with the relational algebra. We can't really do that. But in general, for many purposes, it's equivalent. We can write some relational algebra query to select P equals writer from the original graph and then project just S and O, and we can generate these tables from the original graph relation. So when we talk about BGPs, which are the basic graph patterns, essentially there's an equivalence to join queries, right? So when we take these 2 tables, we can compute the BGP in a relational language as a join between writer and fought, such that the object of writer, is equal to the subject of fought here. Yeah. So now we find writers that fought in something. Yeah. So we get 3 results. So I'm going to keep here the names, the duplicate names, even though these are redundant columns, I'll keep them for a minute. Yeah. So we get the join results, and then if we wanted to compute the final part, we can take these results here, bring them up here, and join them with inspired. Do a join. F.O, the war, is equal to the war, F.O is equal to inspired I.S. The war here is equal. And the subject, the name of the book here, is the same as the name of the book here. And that should give us our triangle. Yeah. So we get this table. Writer, fought, inspired, and there's also a cycle here that the name doesn't represent, but we can simplify now these redundant names to just give the variable names here, because this, for example, the object of writer is the same as the subject of fought, right? We have that equality condition, so we can just simplify it, and these are our results, right, for our basic graph pattern. Is that okay? No? Okay, so we see that there's some relation between join queries and these basic graph patterns, or between the relational world and the graph world, which is not really also too surprising. So I'm going to get into a little bit of a primer for something that we'll talk about later, a more technical topic, which is the AGM bound. So an interesting puzzle, if you're not too tired or too hungry. How many results will the query on the top right, this query here that we saw before, return in the worst case given a graph with n of each type of edge? So if I give you a budget of 4 writer edges, 4 fought edges, and 4 inspired edges, and tell you to create a graph, what is the graph that you could create that would generate the most answers for this query, right? Let's have a look. Let's say n equals 4. We have in total 12 edges, 4 of each, 4 of writer, 4 of inspired, 4 of fought. Yeah. One thing we could think to do as a start, we'll just have our 4 nodes here. Authors, A1, A2, A3, A4. Conflict C1, C2, C3, C4. Books B1, B2, B3, B4. So we have to connect these, yeah, in such a way that we generate the most number of results for this query possible. So one way we could think of starting to do it, let's just do something. Okay, maybe a little bit ugly, but we have B1 connected to A1 connected to C1 with the correct edge labels, right? So we have I as inspired, W as writer, and F as fought. So we're kind of keeping the same overall structure here. So we have B1, A1, A1, B1, C1, A2, B2, C2, A3, B3, C3, A4, B4, C4. They're actually separate. We could just pull them apart. They're 4 graphs that are not connected. How many results will we get for this basic graph pattern here? We'll just get 4. Yeah, we'll get A1, B1, C1, A2, B2, C2, A3, B3, C3, A4, B4, C4. Just in case we have no symmetries or no rotations, because the edge labels ground the orientation of the triangle, right? Does that make sense? So we get 4 results. Okay. Can we get more than 4 results? No. So you're saying somehow try to create 4 by 4 by 4 and connect everything, but that way you overuse your budget. You have only a budget of 4 W or writer edges, 4 inspired edges. Yeah, yeah. So we can only have 12 edges. Yeah. Yeah. So that's the kind of a natural next step, right? So you have an author who wrote 4 books, okay, the direction, fought in 4 wars, and then we connect as best as we can the books and the wars, right? But how many results do we get? 4. Yeah? So we get A1, B1, C1, A1, B2, C2, A1, B3, C3, because we have to connect these. Although we've created these pairs, we have to connect them back with the 4 edges again. Yeah, so we can only pair them off. So we still get 4 results. Can we get more than 4 results? Yeah. So we'll need to do that. We'll need to put A1 and A2 to the same book. Yeah. We can get more. The question is how many more? So you can think about that for a second. We'll come back to that. Yeah. So to explain the answer to this, we can characterize how many we need. And we need to talk about 2 other concepts, edge cover. is as follows. So with the edge cover, we have a graph, and our basic graph pattern is still a graph, right? So we assign to each edge a weight. Yeah. In this case, it has to be a number, and it would typically be 1 or 0, an integer. So we assign, in this case, an edge the weight 1. And what we do is we assign to every node in this edge the weight, right? So we assign author 1 and conflict 1 because it appears in this edge, and this edge has weight 1. In this case, we assign this edge a weight 1, and we assign a 1 to the nodes here, right? Because both nodes appear in the edge. And in this case, we assign a 0. Why do we assign a 0? I'm going to have to explain, but we assign a 0, and that way we give 0 weight to everything. Yeah. We call this an edge cover, this weighting of edges, if the sum of the nodes here gives at least 1 in every case. We've covered all of the nodes. Yep. So this is a valid edge cover. Are there any others? There sure are. We could rather assign this edge and this edge 1 and 1, right? In this case, this will have 2, right? This will be covered twice by these 2 edges. Yep. So this is called an edge cover. It's a little bit unsatisfying that we have to use this 2 here, right? It's like we just want to get to 1, and we've kind of overshot it, but we have no choice. There are other edge covers. We could also add, we have 1, 1, 0, 0, and 1. We could also have 1, 0, 1, right? So this is called an edge cover. We have something called a fractional edge cover, which allows you to assign fractional or decimal numbers, real numbers to as weights. So this is still a valid fractional edge cover. The edge covers are still valid fractional edge covers, but we can do some clever trick here if we're allowed to use reals. In this case, we're just using a fraction. We can assign weights of 1/2 to every edge. And if we assign a weight of 1/2 to every edge, we see that every node is covered by 2 edges, is involved in 2 edges. So 1/2 plus 1/2 equals 1, and we get 1, 1, 1. Yeah. So this fractional edge cover has exactly the same rules, just that here we can have real numbers. And when we add the nodes, we have to get to at least 1. And with the fractional edge cover for this triangle, we can get exactly that. Okay, so why am I talking about all this? We're going to get to the answer to our question soon. An AGM bound then tells us what is the limit of the size of the results we can get for this sort of query, given a certain size of graph. So it is actually defined for relational databases, but here I'll talk about it in the graph setting. So we have a graph. We have some graph. We have the number of edges of each type. Here I have F for fought, I for inspired, and W for writer, just to base it on the example. We have the fractional edge cover in Q, which are these values here. So this is WF, this is WI, and this is WW, unfortunately. So it's 1/2, 1/2, 1/2. Yeah? So what is the equation? We have this inequality, which says that the number of results for this query over a graph with this size must be less than or equal to this equation here, which is the number of edges to the power of the weight in the fractional edge cover. Yeah? So what does this mean in this case? It means that we have 1/2, 1/2, 1/2, so we replace the weights. And if we assume, as we did before, n equals 4, we assume that they all have the same size, just to simplify, right? Then what we'll have is that the number of results will be less than or equal to n to the power of 3 over 2. That would be, in our case, 4 to the power of 3 over 2. Yeah? Assuming that these all have the same cardinality, which is just to simplify for the example. Yeah? So what's our answer? So let's say we saw this question of what about n equals 4? 4 to 3 over 2 is 8. Yeah. So it's the square root of 4, 2 to the power of 3, 248. Yeah. So there is a graph that produces 8 results for this query. And this whole analysis here gives us a hint that we somehow have to use the square root of something. Yeah?
I mean, the graph that was mentioned, but it's also within the natural thing having two authors, 2 wars, 2 books, and then because you get the same answer for both graphs.
No, that intuition is good, I think. I'm not sure I fully understood, but that's the idea. If we want to produce 8, what we have to do is take the square root of 4 and then connect pairwise the square roots. Yeah? So what we'll do is, can we get more than 4 results? We sure can. I'm just going to ignore A2 and A3 here. So this is more visually aesthetic, so it's a little weird, but A1 and A4 are the ones we'll use. It looks nicer as a graph. Okay, so we have A1 and A1. We connect to all of C1 and C4. A4, we connect to C1 and C4. C1 and C4, we connect to B1, B4, B1 and B4, we connect to A1 and A4. So we ignore 2 of the nodes. We just use 2, and then we connect them pairwise. So they're all connected, and that creates 2 by 2 by 2, 8 results. Yeah. And you can see the relation maybe to the 3 over 2. Yeah, it's like take the square root and take the power of 3. So here's our results: A1, B1, C1, A1, B1, C4, A1, B4, C1. So we get all the combinations of the 2 A's, the 2 B's, and the 2 C's as results. Yes, we get 8 results. And 8 is the maximum. We know from the AGM bound that there can't be, we're not going to find a better graph or a graph that generates more answers. Let's say n equals 9. What would we get for this? What would be the max? Square root of 9, 3. 3 to the 3, 27. Yeah. So here I didn't draw the 9 nodes, I just used the ones we use, but here it's a little bit clearer, maybe the visualization. Yeah, we take the 3 nodes and we connect them all 3 by 3 by 3, and we get 27. And we are still within our budget of 9 Wright's edges, 9 Spire's edges, and 9 Fought edges. Okay. What about this query for n equals 3? How many results could we get? We could go through the edge cover thing, but I mean, I can explain that afterwards, but Fine. Yeah, so we connect everything to one author, and now we get all the combination of the 3 B's and the 3 C's. So we're going to get 9 results, right? So we just have one A2. I just use A2 because it's the most aesthetically pleasing. We use A2 and we get B1, C1, we get all the combinations of B's and C's. Yeah. So we see that even just for n equals 3, we're breaking the bound. By removing this extra edge, we're actually getting more results now. And this is n equals 3, not n equals 4. So we get quadratic. Why is it quadratic? If we look at the edge cover, we have to assign a 1 here to this edge to cover book. And we have to assign a 1 here to cover conflict. We have no choice. So then it's n to the 1 times n to the 1, which is n squared. Yeah? We don't have this extra edge, so we can assign halves to everything. So this is 9. N equals 4. We changed the graph. Now we have a square. I tried to keep with my ABCD theme with the disaster, but I don't know. It doesn't really make much sense, but we have an author present at a disaster that originated at some conflict that was inspired the book where the author is a writer. What happened? Okay, well, this is the graph that produces it. So what is it? It's n squared. So what we're doing is we can assign a half here and a half here and a half here and a half here. And that covers all the nodes. So that would be n half times n half times n half times n half, which is n squared. Yeah. And this gives us the same idea where we take the square root of the nodes and connect them pairwise, right? So we get the 2 by 2 by 2 by 2, which gives us 16. So these are not all the results. There's a ... there. It's too many to show. We could also do this another way. We could say rather than assign a half here and a half here and a half here and a half here, we can assign 1, 0, 1, 0. Yeah. So we assign this this edge here a weight of 1. This one is 0. This one a 1, and this one is 0. And what happens then? One might ask what happens if we take n equals 5, then we have a rounding problem, right? But okay. So if we take 1, 0, 1, 0, we get something like this graph here, where we can just take one A1, connected to 4 Ds, connected to 1 C, connected to 4 Bs, and we get all the combinations of the Bs and the Ds. And that gives us, again, n squared. Yeah, and this works as well for cases that are not square. So this bound is tight. This ACM bound is tight, meaning that we can construct a graph that gives us exactly what the ACM bound predicts, which is the kind of cool thing. So in this case, 16 results. No more AGM bound. I think in the interest of time, I could probably talk about this on day 3. I might push this to day 3. So you have some background to start to understand a little bit. What I was going to talk about was how we can get algorithms that that approximate or that can evaluate the queries in time proportional to the AGM bound, worst case optimal algorithms. So they don't take any longer than the number of results that the AGM bound predicts. Just as conclusions, graph databases are a hot topic. We spoke about 2 models very briefly about property graphs and focus mainly on the simpler graph. Query features, we have basic graph patterns and path queries, and we can also mix in the relational algebra. Need for efficient methods for evaluating queries in time and space. And this is the topic we're going to start to get to in day 2 and 3. So you have a kind of an overview, some conceptual ideas, and we'll get into like how do we index the data, how do we can we use compact representations, what sorts of time complexities do we need for worst case optimality and so forth. So worst case optimal join algorithms, which I didn't really talk about in too much detail, I'll postpone that part, but they're a promising advance. So coming up in part 2, Domagoj is going to talk about a graph database system that we're developing in Chile. So we've been collaborating a lot with Diego, with Gonzalo, Domagoj. I don't know if there's any other collaborators here in Millennium DB. Anyone I've forgotten? No? So we've been working together on a graph database and using different techniques there. So Domagoj is going to talk about the paths, how to evaluate the paths. And in part 3, I'm going to talk about a compact graph representation based on wavelet trees that we can use for evaluating WCO joins, worst case optimal joins. Yeah, there's some references here in case. So that's it for day 1.
Thank you, Aidan. Questions? No? Okay.
Everyone's hungry.
Yeah. Lunch now? Jose, do you want to say?
Yeah, what's the plan now? We have lunch in a restaurant that is very close from here. So everyone go with me. We'll be the same restaurant every day. So at the same time, let's go. It's called Kibus, just in case, but it's half of a block from here.
And just as a side note, both the previous work and our algorithm does a single pass over n and runs an expected linear time in n. So it is essentially a streaming algorithm. Now, what is this parameter d that appears in the optimal space bound? Like I said, we now focus on the left minimal co-occurrences problem. We named the function LMCO, and it's exactly the same as the one I showed you, only with the added restriction that the co-occurrences need to be left minimal. We define this function delta, which is simply the difference encoding of the LMCO function. So delta I is simply the number of left minimal co-occurrences of length I minus the number of left minimal co-occurrences of length I minus 1. We define the set SED to be all the integers I such that delta I is not equal to 0. And we simply define D to be the number of such I's. What that means is that the optimal space consumption is linear in the number of changes you see in the LMCO function. Okay, so I will not go into the upper bound here because it is only a marginal improvement on the previous work. Instead, I will go into the structure of this delta function, and then I will show how we use that structure in order to prove lower bounds for the problem. So we say that a co-occurrence is minimal if it is both left and right minimal. And here, right minimal is of course analogous to left minimal. We denote the minimal co-occurrences like this in increasing order by their rightmost endpoints, as you can see here. So this is a unique order because at most one minimal co-occurrence ends at a given position. And we note that if you take two adjacent minimal co-occurrences, that is Li, Ri, and Li plus 1, Ri plus 1, they're either staggered like they are on the left, or they're completely separate like they are on the right. You can never get into the situation where one completely covers another, because of course, then it would not be minimal. So consider some specific minimal co-occurrence here, Li, Ri, and also consider the endpoint of the next co-occurrence. What we want to show is that all the strings here that start at Li and end at the positions starting at Ri and up to, but not including Ri plus 1, that all of these are left minimal co-occurrences. So consider some specific index k between Ri and Ri plus 1. Well, of course, the string starting at Li and ending at k is a co-occurrence because it contains a minimal co-occurrence. And if you take away the leftmost character, that is the one at index Li, then you no longer have a co-occurrence. So we prove this by contradiction. Suppose that this is a co-occurrence. If it is a co-occurrence, then it must contain some minimal co-occurrence, which you can obtain by simply shrinking the co-occurrence. And because minimal co-occurrences are staggered or completely separate, like the way I showed you earlier, that means that this minimal co-occurrence needs to end between Ri and k. But then it also ends between Ri and Ri plus 1, which by definition is not possible. So this Li plus 1 to k is not a co-occurrence, which means that Li to k is a left minimal co-occurrence. Okay, so now we know that for any given minimal co-occurrence, all these substrings here are going to be left minimal. So each minimal co-occurrence contributes one left minimal co-occurrence of each of these lengths. So the length from Li to Ri, and that length plus 1, plus another one, and so on and so forth, up to, but not including the one starting here and ending there. And in fact, if you just do a little bit more work, you can actually prove that the number of left minimal co-occurrences of length W is equal to the number of minimal co-occurrences such that these two values here, this len Li Ri and len Li Ri plus 1, straddle the W, right? So And this actually gives us what we need in order to define the delta function. So I give you the definition first, and then I explain why it is correct afterwards. To get the kth entry of the delta function, we simply sum over all the minimal co-occurrences, and then we add 1 if the length of the co-occurrence is exactly k, and we subtract 1 if the length from the start of this minimal co-occurrence to the end of the next is equal to k, and otherwise we do nothing. So why is this correct? Well, remember that I defined the delta function to be the difference encoding of the LMCO function. So to get LMCOW, you simply sum over the first W delta entries. Now, if the minimal co-occurrence LI, RI straddles W in the sense that I explained on the previous slide, well then length LI, RI is going to be on the left here, and this other length is going to be on the right. So we get a +1 contribution to delta on this side, and a -1 contribution over here. And we only get the +1 contribution in the sum of the first W entries. So we actually account, or this minimal co-occurrence contributes +1 to the sum. However, if the minimal co-occurrence does not straddle W, then both of these contributions are either on the left or on the right side of W. And in the top case here, they just sum to 0, and in the second case, they're not included at all. So with this definition of delta, we exactly count the number of minimal co-occurrences that straddle W, and therefore we get the correct value for LMCO. Okay, so now I'm going to show how we prove some of our lower bounds. And the way we do that is by carefully constructing instances that encode information in the delta function, and then we use the information theory, or we just use sort of information theory to give lower bounds on the representation. So this is the increment gadget. We define Q to consist of A and B, and we have some universe U of integers starting at 2, and we define the gadgets GI as follows, where $sign is simply a character that is not in Q. Note that the length of the substring starting at the A and ending at the B is exactly I. So if we concatenate 2 of these gadgets, we get this string right here. Consider the minimal co-occurrences that start in GI. There's one starting at A and ending at B, and there's one starting at B and ending at the next A. Now, if we consider how these contribute to the delta function based on what we just said, right, we're going to get a +1 contribution for this minimal co-occurrence, a +1 for this minimal co-occurrence, and then -1 for these other 2, from the start of one to the end of the next. And if you calculate exactly what these entries are, you get a +1 to delta I, and all the other contributions are to delta entries that are larger than U, right? So all of the other contributions are to a range of delta that is outside the range of our universe that we defined up here. So if you give me a sequence, P2, P3, PM, it starts at P2 intentionally here, consisting of elements from the universe, I can encode it in an LMCO instance as follows. We take P2 concatenations of D2, P3 concatenations of G3, and so on and so forth. Then by the stuff that we said on the previous slide, delta I equals PI for each of the I's for each PI in the sequence. And that's simply because we increment delta I that many times by having that many copies of the gadget, of course. And by definition, delta I is simply the difference of 2 LMCO values. So if you have a data structure that can calculate LMCO, well, then you actually have access to the delta function. And since you have access to the delta function, you have access to a representation of this sequence that we started out with. Now there are approximately U to the power of M sequences, which means that you need M log U bits to represent it in the worst case, which is on the order of M words. You can actually show that M and D, right, the number of unique entries of delta that are non-zero, are actually asymptotically equivalent here, which gives that in the worst case you need omega D space. So that's the lower bound on space. Now the last slide here, I'm going to show you how we get a lower bound on time. So let x be a set of integers from our universe, and let them grow from x1 to xm. As I'm sure you all know, the predecessor problem is to, given some y, find the largest element in your set x, which is no greater than y. We're going to encode this instance of the predecessor problem in the following string. We have x1 occurrences of gx1, x2 minus x1 occurrences of gx2, x3 minus x1 occurrences of gx3, and so on. So let xp be the predecessor of y and x. Then if you calculate LMCO y, that's simply equal to summing over the first y delta values. But we know that most of the delta values are actually zero. The only ones that are not zero are these x1, x2, x3, so on and so forth. And we know what these are. The first one is x1, and the second one is x2 minus x1. The next one is x3 minus x2, and so on and so forth. This is just a telescoping sum that evaluates to xp, which is equal to the predecessor of y. So if you have a data structure that supports LMCO on this instance, then you actually also have a solution to this predecessor problem instance up here. Now, if our LMCO data structure uses order v space, then you get a predecessor data structure that just uses order m space. That's again by this equivalence of m and d from the previous slide. And there is a lower bound by Petrashka and Torup that says that for certain choices of u relative to m, and for data structures that uses near linear space, you actually need omega log u time for queries. And in this case, the length of the string is approximately u squared, so we get this log square root m time lower bound, and the square root disappears due to the log. So that is how we prove lower bounds on time. That's what I had to say. Any questions?
Any questions? Any questions on the Zoom? No? Okay. Yeah, I didn't. Can you show me the result on your first? I think the early slides. Yes. So yeah. So I didn't. So I want when I read this, I wanted to ask if your results also this, I mean, what is the word? I mean, does it, is it possible to use more space and get a faster result? But I guess it's not, because you reduce it to predecessor and things. So yeah.
Well, I mean, so there is a like a full trade-off curve based on the reduction that we use, which will, which I think if you just think of if you allow yourself to use space as a function of d, which is not necessarily linear, but maybe something else, then yes, you would get a better running time, because in reality, our data structure is literally just a predecessor data structure on this set Z, right, of non-negative delta values. So if you just use more space, then the predecessor structure gets better and you get faster query times. But it's limited how long that is interesting because, of course, if you use linear space in the length of the string, then you can just store all the LMCO values and get constant time queries. So you need to be careful that you don't use too much space, essentially. So if the function in D grows too fast, and D is it can be pretty close to this squared n thing, then all of a sudden you're using superlinear space, and it's no longer interesting.
So also, have you implemented this thing or?
No, we have not.
Okay.
We have not implemented it. No.
Okay, thank you. Any other questions? Okay, let's thank Tor.
Thank you.
So the last talk, this is on-site talk, or is it online? Ah, there you are, sorry. The last talk is reconstructing parameterized strings from parameterized suffix and LCP arrays, and the talk will be given by Aidan.
Thank you very much. My name is Aidan Konratowski. I'm a postdoc at Waterloo University. And let's start. So it's a joint work from my colleagues. I'm going to see how to use this. Okay, sure. Okay. No, I need some help with it. Yes. Thank you. So joint work with my colleagues, and we are going to talk about reconstructing parameterized string from a parameterized suffix in LCP arrays. So the motivation is the following. Not sure. Okay. So the motivation for parameterized matching, some of you might know it, some of you it's new. So the idea is that we want to detect that three images are the same. And we want to say that they have the same structure but different colors. So we want to say that we don't care about whether or not the color map is equal between the images. Another example is detection of code duplication. Let's say that some students use the same code, and what they did, they only renamed the variables. So for example, here we have int x equals 5 and a printf of this x, and here we have the same code, but the variable name was changed. So we want to detect such renaming as well. And for this, we have a parameterized matching, and the parameterized matching works as follows. We have a static characters, parameterized characters, and what we say is that the static characters are going to be the same as we go, but the parameterized characters are allowed to change them, and we restrict that we have to have a bijection. It means that all A's go to another letter, all B's go to some letter C, and all the remaining letters go to the remaining letter. So we can see here that these two strings are matching because all the red A's goes to the B's, all the blue B's goes to the blue C's, and the static letters remain the same. So, and in the previous examples, it captures the natural matching. It's the normal matching in which A equals A, B equals B, C equals C. It matches if the parameterized alphabet is the empty set. Captures the color maps that we saw previously in the slide. If we don't have static characters, only the colors themselves. And it captures code duplications if we define the static variable to be all the fixed tokens and pi to be the variables of the program. And we are going to use during the talk some encoding that it's called the prev encoding. In this prev encoding, we transfer each letter to a number, each of the parameterized alphabet, and fixed letters or static letters remain the same. So we can see here that if a letter is a static letter, we keep it the same. If it's a parameterized letter and it's the first occurrence of it, we put 0. And if it's the second occurrence or other occurrence of the same letter, we put a distance to the previous occurrence of the same letter. So for example, here, in this A, we put 2 because it's the distance to the previous A. In this A, we put 2 because it's the distance to the previous A. And here we put 4 for this B because it's the distance to previous B. For the first A and B, we put a 0 because they don't have a previous occurrence. And the problem goes as following. So what we want to do, we want to input a PSA and PLCP array. So a PSA is an array in which we have the suffixes sorted, but it's not the usual suffixes. It's suffixes after we apply a prev transformation on them. So we apply prev transformation on each suffix, we sort them, and this is the PSA. A PLCP is the LCP between each consecutive 2 suffixes, and we can see here that we have n minus values. And the way that we define it is the input of the problem is only, we have these only numbers of the PSA and PLCP, and we want to recover what was the original source text without knowing what was before. So we only have these numbers in hand. And what we are going to see is that this problem is going to be harder than the normal problem because we don't have any relationship. The relationship between substrings are more complex than in the natural matching. Let's talk about previous work about this topic. So previously there was some results about how from the suffix array it's possible to recover the original string from the dynamic acyclic subsequence graph and also directed acyclic word graphs. So there was a lot of work also from the BWT and suffix array, and also from the suffix tree with some restrictions, but with assumption that we have suffix links. So it's a pretty interesting work. And in our work, what we managed to do, we assume that we have the PSA and PLCP, and we managed to recover in n squared time and space what was one of the original strings that created those suffix arrays. The naive approach would take exponential time because it's the number of strings. And in the general version, we will improve it to be n log n. Okay. So during this talk, I will assume that we have strings over alphabet pi. Later, we will see how to observe strings over sigma and pi as well. So our algorithm works as follows. We have the first step of the algorithm called left table. And in this step, we are going to treat equalities and inequalities of the algorithm. By equalities and inequalities, we mean the following. So if we have 2 suffixes, let's say S9 and S12, and these are their values. Of course, the algorithm doesn't know the values, but we know that the LCP is 3. Then we know that the 3 first characters are equal to each other, and the first character is different. And we also know that the order between the suffixes, because we have the suffixes in a sorted order. So in the algorithm, what we are going to do, we are going to use placeholders to indicate that we have some letter which we don't know. Of course, in some cases, we know how to recover if there are 2 zeros at the beginning. Sometimes we know how to recover ones. So this is a practical example from the algorithm. So here we can see that because here we must have a 1, and here we have a G that's less than 1, it must be a 0 here, for example. The second step of the algorithm would be to align the same positions of the suffixes. So if here we assign a placeholder for each position, now we are going to align all the suffixes to the right And this is why it's called the right table. And in this case, we are going to see that, for example, character 15 participated in few suffixes. Sometimes it got a placeholder S, sometimes it's got different placeholders, but it's not necessarily the case that all S, J, and C are the same value, because in the parameterized matching, it might be the case that S is 0 and J is 4, for example, because of the structure of the parameterized matching. And so this is the challenge of this problem. And what we can see is that if we get this right table, there are two possible outputs, which are very similar but a bit different strings. And for us, both of them give the same PSA and PLCP array, and therefore we don't care which one the algorithm reports. And we, of course, we proved it in the paper. So the algorithm outline, we divide the algorithm into five stages. The first one is to fill the left table and resolve the mismatches that following the PLCP. We are going to discuss the two first steps. Then we are going to talk about the right table and the reconstruction of the P string itself. Okay. So here we have the input of the algorithm, PSA and PLCP. We construct the left table. So the idea is that we know where to put 0, 0, and 0, 1 because of the PLCP changes from here, changes it and it's 1. So we can detect this point, and the proof is in the paper. And we assign a placeholder for each letter. And the red letters are the place in which we know that there is an inequality because the LCP ends there. So we have something like this, and we will see now how to transfer it and how to detect what are the values in the red places using, in the paper, it's called algorithm 1. So the idea of algorithm 1 is the following. So let's say that we have two suffixes S1 and Sj. And of course, we don't know which are the values here, but eventually what we want to detect, we want to detect that here we have a 5 and here we have a 3, but without knowing the content. All we know is that we have the PLCP of 6 between them, but we also know something else. We don't only know that they're unequal, we also know the relation between them. So we know that 5 is larger than 3, but we don't know the values themselves. So the idea would be the following. So each time we are going to slice one character from the beginning of the suffixes. And the reason why we can do it is because it's possible to pre-process the PSA and PLCP array to support queries of what is the PLCP between any two suffixes. And here the PLCP is going to be 5. By slicing the first character, what happened is that this A, which had the prev value of 2, now has the prev value of 0 because it's the first prev in this first character in the string. And here is the same. And therefore, because we sliced the first x, here we have a 2. 2 is the distance to the previous x, so 1, 2. But now we removed it, so it's a 0. And the PLCP is 5, but here we still don't have anything to say. We don't know which one is 5 and which one is 3, so we need to continue. We slice another letter from the beginning, but now what is happening, we sliced a B here, but this B is now the first B, so the prev value is 0. But in the other suffix, when we slice the second letter, this Z remains 3 because it points to the previous Z from which its distance is 3. So we can see here what happened is actually we had these two comparisons. And here we have the first suffix was larger than the other. Here we had the first suffix is actually becomes smaller than the other. So from this, we can detect directly that we had here 5, which turns to 0, and therefore recover that here we had a 5. So this is the idea. Now I want to show you how to recover this 3. And the idea is that if we proceed a few more steps into the algorithm, when we slice the first character here, what will happen is that this z, which pointed to the previous z here, and the prev value was 3, now becomes a 0. And because it becomes a 0, the PLCP exceeded beyond these values, and therefore we can detect this value was 3. So because it's the point in which, after which the LCP is exceeded. So this is the general idea of how algorithm 1 works. And in the paper, you can look how it's written in the paper. And basically, it's also possible to make it work in n-log time directly. Okay, so now we are going to talk about the next steps of the algorithm. What we actually showed, we showed how to do step 2 of how resolve the mismatches following the PLCP value. After these 2 steps, we might have some places which we don't know what is the value in those places, but now we have this write table which helps us to detect these values. So the idea is the following. Here we have a write table. What we actually did, we took all the suffixes and we aligned them by the index. So for example, the suffix 1 is here in the bottom, but we wrote it up until the place which participated in the PLCP, because beyond this we don't have any information, so we don't say anything about it. Here the same, it's the second suffix, third suffix, fourth suffix, and so on and so on. What we can see after we write them down, that in some places, the yellow places, we can detect and recover the value. So for example, here we have 2 zeros S and 2 zeros after S, so we know that S is going to be 0. And it's possible to see that for all the yellow places, we can recover the value. For the orange places, we don't know how to recover the value. And it might be the case that we can put there a few values. So for example, in this example, we can put different values, and depending on the value that we put, of course, it must be valid to the prev encoding, but there are 2 possible variations, each gives a different string. And we proved in the paper that if we put in the orange places zeros, it's always going to fulfill the correctness of the algorithm. If the PSA and PLCP were valid, then it's going to be fine to put their zeros. Okay, so what we see this how to fill the right table, and we also talked about how to reconstruct the P string, the final P string. The verification of the algorithm output is straightforward. We just check if the P string that we got is correct by constructing the PSA and PLCP in a linear time. Okay, so the final step of the algorithm is to support. I want to give you the idea how we support the general case of the alphabet without the assumption that we have only pi. The idea is the following. If we look at the PLCP array, we see that there are places in which we have these zeros, and these zeros in the PLCP are actually meaning that we have here static characters x and y, because in the parameterized case, if the first character is parameterized, it's always going to be a 0. Because of the way that prev is defined, because it's the first character there. So once we see zeros, it means that we have a static character, and we also know the index of the static character, 4 and 7. So we know that x is in position 4 and y is in position 7. Of course, we don't know whether it's a x or a y, but we can put there any letter that we want. And the idea is the following. So by performing few LCP queries, we can construct a suffix array without those letters. So the idea is that we remove this X and Y from the string, yes, and we construct a equivalent suffix array and PLCP array, and on which the algorithm is performed. And after we done performing the algorithm on this redacted problem, then we go back and we can recover that here we had characters X and Y, for example. Okay, so further work. So we talked about that we are going to improve the time and space to n log n in the journal version. We had also some results for the recovery from only the PSA without the PLCP array. And of course, if you have any ideas, I would like to hear about any data structures from which it's possible to recover the original input. And yeah, of course, I would like to hear more. And thank you. Yeah. Okay. Yes.
So actually, I have so I have two sort of semi-stupid questions and one really stupid question.
Together make one stupid.
Yeah, no, two stupid questions. So the first one is, I would just guess the n log n speed up, you're going to use like binary search to find where the inequalities swap.
Online people can't hear the answers.
So yeah, the binary search is going to make sure that step 2 is working, but there is also a problem with the right table. So it's more complicated, but yeah.
Another one. Yeah, so another thing, so when you motivated it by determining whether two pieces of code match, I was thinking that if I were a nasty programmer, you could actually sort of defeat that by if you have scope. So if, for example, I have two for loops, and in the original code, they used nice descriptive variable names which did not match. And then I'm going to say, well, okay, but I don't get a scope conflict. So I'm just, every time I enter another subroutine or another loop or something, I'm going to restart my variable counter. Is there some way you could, like, would this kind of thing still work for where you can sort of take into account it's not exactly a bijection, because taking into account stuff like scope?
So it's a good question. I know that in practice, when finding a code duplication, it's enough to get 80% or 70%. It's like people can define how close the code should be. I don't. There are some papers about it, so I don't recall them reading them. But in this context, I would say something like maybe it's possible also to. When a program is written, it's possible to also, there is some optimization step. So maybe if getting to the optimization step and then checking if the code is the same, maybe it's giving more of a feeling like it can get rid of some simple complications, but I don't know, this is my intuition. So maybe it's...
Actually, I don't know, could yours be parameterized? Could yours also be parameterized to deal with something if they said like, it's 80% the same? And the last thing, just since we're on this slide, if it's a bijection, to me, it looks like the penguin's feet in the first two are this actually like monochrome, and then it has shading in the last one. So it's not It doesn't look quite. That I said it was a stupid question.
Yeah.
The right one is shaded, but if it's, I can't see that. It is? Okay.
Okay, thank you.
Any more questions? Or are there any questions on Zoom? Okay. I have one, but I will ask you later because it's time. Okay. So let's thank all the speakers in the session. And now we have a coffee break.
Shall we start, Jose? Yeah, okay. Welcome to the last session of the day. We'll have 3 talks, the first one online and then 2 on site. And the first one is compressed string dictionaries via data-aware subtree compaction, will be given by Antonio Boffa. I think you can start, Antonio.
So, hi everybody, I'm Antonio Boffa, a PhD student at University of Pisa, and I'm going to present you the paper titled Compressed String Dictionaries via Data-Aware Subtree Compaction. This is a joint work with Paolo Ferragina, Francesco Tosoni, and Giorgio Vinciguerra. So I'll start introducing the problem. It is called the string dictionary problem, so it can be defined in the following way. Given a set S of n strings drawn from an alphabet sigma, we want to store them in a compressed form, and we want to implement the rank function. Rank of a pattern of a certain string P must return the number of strings in the set S, which are lexicographically smaller than or equal to P. Through rank, several other classical operations can be implemented. For example, the lookup, the access, the predecessor, and the prefix range. It is a core component of a plethora of applications like query auto-completion engines, key value stores, computational biology tools, anagram language models, etc. Let's see a brief example. So, given these 7 strings, rank of the string this, which is in the set, is 6, because there are 6 strings less than or equal to this in the set. We want to solve the rank query also for strings that are not in the set. For example, sum. The string sum is not in the set, but still we want to, because there are 2 strings in the set which are lexicographically smaller than or equal to the string sum. Classically, this problem has been solved with the trie-data structure. That is a data structure studied since the 60s. It is a simple structure, but it must be carefully designed because there are some critical issues. For example, how to branch in a space and time efficient way. An ideal solution could be to store an array of sigma pointers to the children. So in each trie node, an array of sigma pointers. This solution is fast, but is memory inefficient. So what about hash tables? We could store an hash table in each trie node, but in this way, we don't have an efficient rank. And in both cases, and in general, whatever data structure we put in our trie node, we end up having a lot of cache misses. Actually, a number of cache misses that is equal to the length of the pattern we are looking for, because we are jumping 1 character at the time. And in literature, there are a lot of improvements. For example, about compacting unary path, about succinctly encode the fan-out and the topology of the trie, about varying the node layout depending on the fan-out of the node, word packing the layout in order to solve the problem of cache misses. Also, some cache-aware layouts have been proposed. What we realized is that there are no known solutions that are locally data-aware, that are able to select the best layout for each trie node in a data-aware manner. That's why we introduced a principled data-aware optimization strategy to build compressed tries. The main ingredients are 3. The first one is about collapsing subtries into macronode. Then we will introduce how to succinctly encode these collapsed subtries and a new way of selecting the best subtries to collapse into macronodes, because not all subtries are worthy to be collapsed. The overall outcome of our paper is the COCO trie, the structure we introduced, and it is called it this way because it is a compressed and collapsed trie. Let's dive into the details. So, what do we mean by collapsing subtries? We want to collapse a certain number of levels into 1 single macronode. For example, in the picture, we want to collapse 2 levels of the subtrie routed into the node V in orange in 1 single macronode. Visually, what we are doing is this one. So we have 1 single macronode that has children all the pending subtries that are pending by the subtrie of two levels routed into the node V, and we can see that the characters of the hash labels are 2 and not 1, like the original trie, because we collapsed at 2 levels. Naively, someone could think, okay, the higher is L, the better. And on one end, yes, we are traversing fewer nodes. Actually, instead of traversing length of the pattern we are looking for nodes, we are traversing length of the pattern divided by L, which is great. But on the other end, we have an higher branching factor, so an higher cost on selecting which path to follow. Moreover, we have more redundancy in the edge labels. For example, in the original trie, we had just one E. Here we have to represent 2 different E's. So E appears twice. The research questions that we would like to answer in this paper are the following. The first one is, how does the choice of L depend on the dictionary of strings? We argue that it strongly depends on the actual characteristics of the indexed strings. Then, should the choice of the number of levels to collapse be global and thus unique to the entire trie, or local and thus vary among the trie nodes? Our answer is that we must select it node by node. And in conclusion, can we govern the space-time trade-off given by L? Yes, with our proposed principled approach. Let's see it. So how to encode the collapsed subtries? Let's start with an example. We have this trinode with 4 outgoing edges. It is 4 levels collapsed into 1 micronode. So we have 4 characters into the edge labels. And we are in a bioinformatics scenario. So we have 18 characters as an alphabet. The first thing we do is that we map each edge label to an integer using the formula you can see there. It is a Karp-Rabin fingerprint without a modulo. And so we end up with 4 integers. We represent explicitly the first integer that we call x. Then we subtract to all the other integers the first one, x. And so we end up with this sequence of integers, 6,175, and then 1, 2, and 3. So the first one is represented explicitly, and the others can be represented using a whatever known synth encoding scheme for increasing integers. For example, Elias-Fano, packed encoding, the characteristic bit vector, dense encoding. Actually, we are going to use all of them. So we are going to leverage a pool of succinct encoding schemes. And in the next slide, we are going to see actually how. Here we need to focus on the fact that we are not encoding the LCP. So the 4 A's that are common between all these 4 H labels are encoded just once in the first integer. And then we just need to store the information for the C, the G, and the T. That is actually what is changing here. How to choose the subtries to collapse? We leverage a dynamic programming approach. So we perform a post-order traversal of the trie, bottom-up, in order to assume that while we are analyzing a node V, we have already all the optimal choices for the descendants. And then we evaluate the space usage for each possible number of levels we would like to collapse. So for L between 1 and H, a constant that we can select, we evaluate the space usage of the macro node collapsing that amount of level, plus the space for the descendants. And the space usage of the macro node is evaluated considering all the 4 encodings, Elias-Fano, packet, bit vector, and dense, and then we select the best one. So the best encoding, the encoding that adapts better to the distribution of integers of that macro node. Let's see an example. With L equals 1, we evaluate the space usage of collapsing just 1 level. And so we evaluate the space usage of the macro node plus the descendants. Then we do it with L equals 2, the space usage for the macro node and the descendants, and then with L equals 3. So 3 levels plus the descendants. After this evaluation, we can select one particular L that we call L star, that is equal to the value of L that minimizes the space usage. Then, during a second visit, top-down, we collapse L star levels of the subtree rooted into V. The complexity of this technique is the following. Given n, the number of trinodes, we have a time complexity of order of n h and a space complexity of order of n. We can set h as whatever value, but it must be less than w divided log sigma. W is the machine world size, and log sigma is a log of the size of the universe. We want that because we want to pack h characters into one single machine word. Then I'll introduce you another optimization, and this is about the fact that the alphabet of the edge labels of this particular trinode in the example is 4, and thus smaller than the global one is 18. So this idea is very important because the smaller the alphabet, the fewer bits are needed to represent the branching labels. So while encoding this particular trinode, we can consider the fact that we are using just 4 characters. And so we end up with integers that are way smaller. For example, instead of having 6,175, considering an alphabet of just 4 characters, we end up with 85, and so on, in general, lower integers. This can be done just saving locally a mapping between the global and the local alphabet of the trinode, and then use the local alphabet to encode the branching labels. This is a very important optimization because in this way we can have an alphabet-aware maximum number of levels. Considering the example in the figure, we have an alphabet of 4 characters. If we use a machine word of 128 bits, and this is actually what we do in our implementation, we can collapse up to 64 levels into one single macro node. So during the traversal at query time, we can consume up to 64 characters of the pattern we are looking for just in one shot, in one macro node. And this is extremely effective in practice. Before going to the experiments, I would like to discuss another last optimization is about the space-time trade-off. So we said that the higher is the number of levels collapsed, the faster is the traversal, you do fewer jumps, the slower is the branching, you do higher fan-out. But actually, we experimentally noticed that our compressed encoding of collapsed subtries and our succinct encoding schemes are in practice extremely effective to be navigated. So we can relax the minimal space occupancy by a constant factor of alpha. In this way, we can collapse more level and thus improving query time, just using a small amount of space, more than the optimal, the minimal one. And this alpha we set as 5%, 10%, and 15%. And we will see it in the experiment part. We tested our solution on a variegated set of datasets coming from different scenarios like URLs, XML, protein DNA, and TPCDS IDs. TPCDS is a classic benchmark in the world of database. And these datasets have a very variegated characteristics. So they go from 3 million to 40 million strings. The size is up to 2.7 gigabytes. And we have to notice that we have very long strings. So for example, the maximum length is 16,000 characters. Just one string is 6,000 characters. The first result that I would like to show you is about how many levels are collapsed into macronode. On the x-axis here, we have the number of levels, and on the y-axis, we have the frequency that this amount of level is collapsed. It's actually collapsing into the macronode. On the URL dataset, we have a lower number, so between 1 and 20 levels are usually collapsing into macronode. On the protein dataset instead, we have a totally different distribution. So we have something like a Gaussian. On average, we collapse 30, 35 levels. And then our data structure is able also to adapt to DNA that are k-mers, so very short strings, and to the ED of the ID column of this database benchmark. So the number of levels collapsed into macronode really vary according to the dataset CocoTry is built on. Then we experimented space and time performance of our data structure. The source code is available online on GitHub. And we experimented our performance against state-of-the-art, highly engineered, and widely used implementation of string dictionaries. They are CART, so compressed adaptive radix trie, PDT, that is path decomposed trie, and fast succinct trie. We chose them because they are exemplary of all the available succinct trie representation. And we used a fair and balanced query workload made of 50% strings in the set and 50% strings not in the dataset, properly generated. Let's see the results. Here we have on the x-axis the time in microseconds per query, and on the y-axis we have the space in megabytes used to store the compressed dataset, the compressed data structure. The more a solution is in the bottom left part, the better. And here we can see that our CocoTry with different alpha parameter between 0% and 15% is an extremely fast solution, actually faster than PDT. So on these two datasets, we are on the Pareto curve. Then on protein, we are really near the Pareto curve. CART on this dataset is a little bit better. And in the end, on these two datasets, we are the best solution out there. So we outperform all the other state-of-the-art implementation. In particular, we outperform FST, that is extremely effective with these datasets. So in conclusion, we introduced a new design of compressed string dictionaries that collapsed and succinctly encode properly chosen subtries with a novel data-aware encoding of possibly long edge labels using a space optimization procedure. And the CocoTry, so the outcome of this paper, this data structure, is space efficient, robust and flexible. Unlike other solutions out there, it obtains overall good performance regardless of the dataset. It significantly dominates the space-time performance of all competitors, or is on the Pareto curve or very close to the Pareto frontier of all the other best competitors. As future work, we would like to make our approach more multi-criteria. So here we are just considering the space usage in our space optimization procedure, but what about time, the query time? What about the query distribution? And with this slide, I conclude my presentation. I would like to thank you all, and I'm glad to answer all your questions.
Questions? Travis?
So this one is actually also partly for Gonzalo and other people here. So there's a data structure called a k-square tree, where you also it's for like higher dimensional stuff, but it's basically also a trie. It's a succinct representation of a trie, and it also goes down at different levels and at different nodes. It can vary the degree, and so I was just going to wonder if anybody here, having seen this, could you go? Would this? Do you think this would work on a? Have you seen a k-square tree?
Yes, I've read something about
Oh, okay.
It's about compressing graphs.
Yeah, it's But yeah, maybe this could also be applied because you can also, in theory, you can choose different Ks as you go down the tree. So this is why it's a K-square tree and not just a quad tree or something. So I guess you could also try to optimize K-square trees this way.
Thank you for the suggestion. Yes, I will look into it.
Other questions?
Okay. Hello? Yes, it's working. Thanks for the presentation. This is just more kind of philosophical question maybe, but I was wondering if you maybe consider using some sort of dictionary compression maybe to decrease the size of the topology, because it's like a generalization, but instead of doing this on strings, you do it on the topology of the tree. I don't know if this is something that you maybe think or not.
So about the topology, we already encoded with succinct encodings for trees, but we were looking for some dictionary encoder for the edge labels. We tested some known solutions like repair or something like that, but our succinct encoding scheme that is able to use the actual alphabet of the trinode seems to be better. So, but we are still working on compressing the edge labels, just the first edge, then the other are encoded with the succinct encodings for integers.
Okay, thank you.
I have another question. I understand that you first decide how to encode the root, and then you go to all the nodes of level L+1 and so on. So in a sense, it's a greedy encoding. Have you considered somehow finding the global optimum for which perhaps you would need to encode subtrees where not all the leaves have the same depth? Maybe you would need to encode a subtree where you have leaves at different depths so as to find the global optimum across the whole tree. Have you thought about this?
So you got it right. It's a greedy approach. So we are locally minimizing the space, and we think finding a global solution is very hard because every choice changes everything, and so we are working on that. But it seems very hard to find a global optimal solution.
But it can probably be handled with dynamic programming, no? Because you have a tree. So it could be done efficiently. I don't know how efficiently, but not so
Thanks.
bad. Yeah.
Yes.
Other
we
questions?
can think a little bit more about that.
Yeah. Other questions? Okay, thanks, Antonio, again.
Thanks.
Okay, our second talk will be given by Eitan, I suppose. It's internal masked prefix sums and its connection to fully internal measurement queries.
Okay, so I think you missed me, so I'm back. Okay, so it's another paper. It's the last one, I promise, for this conference. Internal masked prefix sums in its connection to the fully internal measurement queries. It's a joint work with the team in Canada that I worked during my postdoc. And I'm Eitan. I will present this paper. So what is the problem? So we have two arrays. One array of numbers, let's say 1, 0, 2, and so on and so on. We do assume that they are non-negative to make sure that everything is well defined. And the second array will be an array of bits, which represents a mask, but we would say that it's a reference mask. It's a large mask. It's much larger than the text itself. and it's going to be of length m. And the array of numbers is going to be of length n. Okay, and we want to support the following query. We want to support the query that we choose a subarray within the mask. So this is the reference mask. We choose a subarray, let's say from this 0, 0 until the end of the orange space, like everything here. And we want to apply the mask on the array A and sum what are the numbers against the ones. So I can see here that I have some mistake in the presentation. So we shouldn't sum this one because against this one there is a 0. But all the other green places, we should sum them because they're against the ones. So the sum here should be not 11, but rather 10. But in the problem, we have a prefix. So what we actually going to do, we actually going to support a bit different query. We are going to support a sum of the prefix. So we are giving a subarray of the mask here, and we are going to support the prefix of the numbers against the ones in the mask array. Again, here is a problem. We shouldn't count this one, so the sum should be 2 instead of 3. Okay, and this is just to make everything formal. So the maximal sum is going to be, we can assume that we are fine in the context of the RAM model, and we wouldn't use more than 2 words of space because the maximal sum is going to be n squared. If you assume all the numbers up to n, the value of all the numbers is limited by n, then the sum is limited by n squared. And sometimes during the paper, we are going to use a U to represent the universe size. And then the RAM model word is going to be log of U, just to make it clear. So what are the motivations for such a problem? So first of all, we would see in the end of the presentation that there is a reductions to the fully internal measurement problems, and we are going to talk about them soon. And so let me show them. The first one is the Hamming distance, fully internal Hamming distance. What does it mean? It means that given 2 strings, we want to query for any substring against any substring and get the Hamming distance between them. So both substrings must be of the same length. So for example, here, ABC against ABA, the Hamming distance is 1 because there is a mismatch in the last letter here. So the idea is that we preprocess 2 strings and we want to support any Hamming distance between any 2 substrings. So this is the first problem. The second problem is the full internal exact matching with wildcards. So here we are interested in how mismatches we have, and we allow wildcards. For example, here we don't care what is the letter against the wildcard, and we have only one mismatch, which is C against A. And it's the same. We want to preprocess 2 strings, and given any 2 substrings, we want to support to count the exact matching with wildcards. So we would see how to make a reduction from the problem that we discussed. So it's possible to do a reduction from this problem to the full internal measurement problems, and we will see it. And another motivation, we can think about the reference mask as a pre-trained mask. So maybe in some sense is the following. So if we're given a mask which the algorithm doesn't know, it will take omega of k time just to read the mask because we don't know what are the values inside the mask. But if we are asking a substring of the mask, maybe it's going to give us a faster preprocess time. And we will, in the paper, we show that indeed we can do a trade-off on the query time and improve it compared to k. So this partial prefix sum problem is it's a folklore problem. It's also known as scans. And the problem is, originally, as the way it defines, we're given only one array, which is array of numbers. And we are interested in the partial sums of this array. So for example, here we sum the first two numbers, here we sum the first three numbers, and so on and so on. In the last cell, we sum all the numbers. So it's the partial array of this array. And this prefix sum is very useful in the context of succinct data structures and also in parallel algorithms. It's used as a block, it's a data structure block of these algorithms. And it's also implemented in GPU hardware. So it's very useful algorithm. It's like, it's a very old results. And of course, there are some new results as well, how to make this data structure succinct. So the results in the paper are going to be the following. So we are going to cover some of the results. We are showing some trade-offs between time and space, conditional lower bounds, a dynamic version of the mask prefix sum, approximate prefix sum, parallel algorithms. Then we are starting to talk about the sparse version of the inner product. So it's the same problem, but when the values are very sparse. And we are going to discuss it later. So let's start with these results. So I'm going to skip it, but it's basically what it says, that we have a trade-off between the query time and the space and the preprocess time of the algorithm. And we will show now a conditional lower bound that shows that the trade-off is tight. So the idea is that of the conditional lower bound is to use Boolean matrix multiplication. And it works as follows. So we given two matrices. We assume that the dimension of each matrix is n divided by 2 squared. And the query is to find the given, we want to find the Cij, which is, C is the matrix of when we multiply A by B. Okay. And the reduction goes as follows. So we take matrix A, we take matrix B, we write the columns of A and the rows of A and the columns of B. And what we are going to do, we are going to perform two mask prefix sum queries. The first one is going to, eventually what we want to do is to multiply all the numbers in row 2 with the numbers in column 3. Because we said that it's a Boolean matrices, the values are 1 and 0s, and therefore, if we multiply them and sum the values, we actually get an inner product, and this is the result of the algorithm. So if we manage to multiply these two columns by rows, because it's 1s and 0s, so we can think about it as putting 1s and 0s. And what we actually do, we query for the green range against the green range here. And then we deduct substitute the black range from here. And this is the way for us to get the value that we want. So we can see here that we computed C to 3. And in general, we can generalize it to compute any Cij. So how it helps us? So for the Boolean matrix multiplication, we have a lower bound of n into the power of w. So it's the best known result that we know. Because the reduction is working for a square root of n. If we put instead of n square root of n, we get n to the power of w divided by 2. And it's possible to show what can be done using this result. But what actually is known is also known that if the algorithm is a combinatorial algorithm, then the best known result for a Boolean matrix multiplication is actually n to the power of 3 divided by some polylogarithmic factors. And therefore, if we put n to the power of square root of n, we will get n to the power of 3 divided by 2. And this is actually the lower bound that we use. We assume that our approach is combinatorial, and therefore we have a combinatorial lower bound of of n to the power of 3 halves. So this is the lower bound. And this lower bound matches the trade-off, the space-time trade-off in some cases. And we discuss it in the paper. So now I'm going to go and talk about the how to approximate this result. So we are going to simplify it. We are going to assume that the approximation ratio that we want is actually 2 by assigning epsilon to 1. And the idea is as follows. We are going to fix an offset in the bit vector B. So we had these two vectors A and B, array A and bit vector B, or a mask. And what we actually want to do is each time that the sum proceeds to the power of I at the first time, we are going to store the position of the sum. But otherwise, we are not going to store the sum. And what it actually gives us, the idea is that if we have a bit mask B and we have some, the mask starts at position I because we fixed an offset. Now we start comparing against A and we start computing the sum of each element. And when we reach a power of 2, we put an anchor. And then the next time we reach the next power of 2, we put another anchor, and so on and so on. And this will actually give us the ability to give a 2 approximation, or in general 1 plus epsilon approximation, if we change the power here instead of 2 to be 1 plus epsilon. Okay. And I'm going to skip the parallel algorithm due to time. Okay, so now let's talk about how to work with the sparse arrays. So in the sparse arrays, we assume that array A and B are loud. Array. Okay, now it's okay. Okay, we assume that array A and B are sparse. It means that there are many zeros, but we only care about the values themselves. And what we can see here, we are going to use the predecessor data structure, in which we just say to the data structure, give us the next value that is in the data structure, and this is the query time. We can assume that it's fast, yeah. So let's see how we treat this problem. So first, let's introduce the set disjointness problem. In this problem, we have a family of sets such that if we sum the number of elements over all the sets, we are going to get n elements overall. And the query is that given any pair of sets, we want to determine if there is an intersection, empty intersection, or is there elements in the intersection between the two sets. And there is a set disjointness conjunction that says that it's impossible to preprocess it better than n to the power of 2 and get a query time better than square root of n. So, of course, it's possible to look at the details and see how exactly it's written, but this is the idea. So the idea is that it's impossible both get n to the power of 2 and get n square root of n. So either one of them we need to pay. And there is a strong set disjointness conjecture which says that it's not only that in one edge we have n to the power of 2 and on the other edge we have square root of n. We also have this trade-off that says that if the query time is x, then the space that we need to use is n squared divided by x squared. Sorry, I didn't mention it's the trade-off between query time and the space that's used by the disjointness, and same here. So here we also talk about the space. And what we actually want to show that there is a reduction from the set disjointness problem to our problem. And it works as follows. So we start from here with the set disjointness problem. We have a family of sets, F. And what we actually know that union of all the sets is n elements, yes. And the way that we are going to construct the data structure is the follows. For each set, we are going to assign n places, and we are going to turn so all of them are going to be zeros, but we are going to turn once only the places in which the element exists in the set. So each element gets, so we know that we have at most n elements, so we need only n places. And the idea is that, yes, this array is going to be in a size of n squared, but because this array is sparse, we only care about the number of bits in the array, which is n. And given such an array, we can use the same approach that we saw previously to compute the difference between two masked prefix sums. And in this way, we can compute, for example, the number of ones against the number of ones in a set. And if this number is 0, then the intersection is empty. And if this number is not 0, then the intersection is not empty. So in this example, we can see that if we subtract the green masked prefix sum and subtract the brown one from the green, we left with the set intersection of S2 and the set intersection of S3. So we intersect both of these sets. And what it actually does, it tells us how many elements are in the intersection. And therefore, what it actually means, it means that it's given that the set disjoint conjecture is true, it's impossible to solve our problem better than in X. If the query time is X, then we must use n squared divided by X squared space to solve our problem. So what we actually got, we are getting the feeling that the problem is hard and it's hard to solve it. And we also show that it's possible to, this bound is also tight. So this is the idea. Okay. So the next thing that we did in the paper, which I'm going to skip, but just to say in a few words, we showed that in the dynamic sparse version, there is a connection to the three sums and the three sum problem, and we show a reduction from the three sum to our problem to show the hardness of the problem. And then we show that the lower bounds are, we have a tight algorithm up to logarithmic factors to the lower bound of three sum. Okay, so now I'm going to talk about the full internal measurements queries, the Hamming distance and exact matching with wildcards. So what we are going to, we already defined them, so I'm going to skip the definition. And we are going directly to the process. Yeah. 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 Yeah, exactly. Between any pair. Yes, please. Oh, louder. Sorry for that. Yeah. Okay, so now you can hear me. So we are going to go directly to the proof, and we are going to prove one of the cases. And the case that we are going to prove the case in which we are go from the internal inner product. So this is our problem, and we are going to show how if we can solve the internal inner product, then we can solve the internal Hamming distance. In the paper, we prove all the four directions. So in the paper, we have two problems, internal Hamming distance and internal edit exact matching with wildcards. And we show a reduction from our problem to both of them, and from both these problems to our problem. And this means that if one can solve either one of the problems, then he or she can solve any of them. Okay, so how we do so? So what we are going to do is the following. So assume that we have an array A and array B. All the ones in array A are going to be translated into 0, 0, 1. All the zeros in array A are going to translate into 0, 1, 0. Okay, in this case, we assume that we have the internal inner product. So in inner product, it means that the array A consists of only zeros and ones instead of general numbers. Here, all the numbers in B are all the ones in B are translated into 0, 0, 1, and all the zeros in B are translated into 1, 0, 0. And this is how we build a new array A and a new array B. And now we perform an internal Hamming distance on these arrays. But what we can see is that if we had a 1 in A and a 1 in B, then we have 0 mismatches. So this is actually the case here. If we have 1 in A against 1 in B, then we have Hamming distance of 0. But for all the other cases, let's say if there was a 0 in A and a 0 in B, we don't want to count it as an internal match because we don't have a 1 against a 1. So we don't count it as internal product. In this case, we can see that the Hamming distance between those two strings are 2. And in general, for all the other combinations, the Hamming distance is going to be 2. And therefore, it's possible to count the number of the ones against the ones. And therefore, we solve the internal linear product using the internal Hamming distance. And it's possible to solve all the problems, and the reduction is found in the paper. So in general, we saw some of the results. We got the feeling of the results that found in the paper. You are more than welcome to read and see by yourself. And thank you very much. If you have questions. Questions?
Sorry, it's just a stupid question. So when you're with total size n equals something, that should be a sum because S is the size of the set, right? Yeah, it's not the union of S, the size of the union of S. Oh, yeah, sorry. Thank you.
Okay. Other questions? Okay. Okay, no more questions. Thanks again. Okay. So the last talk is by Travis on representing the degree sequences of sublogarithmic degree Wheeler graphs.
So, scary title, but it's not a scary talk. How do I? Okay, this thingy. Ha, ha, ha. Okay, good. Can I be full screen? Doesn't matter if not. Okay. Oh, cool. Okay, I go back. Okay, so as I said, this is the scariest part of the talk. Is the title. Okay. Okay, good. Okay. Okay. So there has been a lot of work on representing Borers-Wheeler transforms compactly. If you don't know what a Borers-Wheeler transform is, I'm sorry. There has been some work, actually quite a bit, on representing standard de Bruijn graphs. And by this, I mean de Bruijn graphs as originally defined years and years ago, but in bioinformatics. So, you have all the k-mers of some set of strings. There has been a little work representing Wheeler graphs compactly. If you don't know what a Wheeler graph is, you can think of it as sort of a generalization of a de Bruijn graph. And there has been almost no work on representing the degree sequences of Wheeler graphs compactly. So what works there has been, it's been basically sort of a Wheeler graph is like a Borers-Wheeler transform and a sequence of in-degrees, of out-degrees, and a sequence of in-degrees. And most of it has been focusing on the Borers-Wheeler transform part. So why do we care about these Wheeler graph things? Well, it's this problem of choosing K, which has come up before today. So suppose we have some reads. Is this the pointer? Yeah, okay. We have some reads, gatag, tagat, gatak, and akata, and they come from this toy genome, gata, gata, kata. And so if we're trying to assemble this genome, and we say, oh, we're going to use a De Bruijn graph. If you don't know what a De Bruijn graph is, well, you haven't been paying attention. So we're going to try a De Bruijn graph of order 2. The problem is this graph has a lot of Eulerian tours. Okay. So it doesn't actually tell you how to reassemble. You don't get this out of this. You can. It's definitely a Eulerian tour, but it's not the only one. So you'd be like, oh, well, that's 2 was too small. We should have tried 3. Problem is 3, this graph is not Eulerian. Okay, it's not strongly connected. You can't, you can do this, but you can't get from here over here, and you can't get from here to this one. So what do you really want to do? Well, if you've been paying attention, you know that you want to have like a mix of 2 and 3. So you want to have something like this, where most of these nodes are 3, but here you have 2, okay? And then it is Eulerian, and in fact, there's only one Eulerian tour. You start here, go there, go back, go here, go here, go here, and you get the genome, okay? So this means that this is why we want to have this variable order De Bruijn graphs or iterative whatever. So you don't want to just have to fix 1K. So that's why you would want to consider a Wheeler graph, right? Because this is not really a standard De Bruijn graph. It's not only 1K. It's so Lin and Pevsner called these manifold De Bruijn graphs. So I guess Pevsner gets to say what a De Bruijn graph is. So maybe this is a De Bruijn graph, but it's not a standard one. But it is still a Wheeler graph. So you can represent a Wheeler graph like this. This is, look, it's here's 2, but the rest of these are 3. So what you do is you take the vertices, you put them in colexicographic order. So these 2 sets of vertices, this is just a set of vertices written twice. And then I've just done it so that you have the A's are green the T's are green arrows, the A's are blue arrows, C is red, and G is orange. Okay. So you can draw these, and look, if you look carefully, lines of the same color can't cross. So if you write the labels on the edges, on the out edges, well, then if you write the labels on the in edges, because the vertices are colexigraphically sorted, the labels on the in edges are just are also sorted. So it's all the A's, the C's, the G's, and then all the T's. So this just works like a Burrows-Wheeler transform. And then what you have to do is, in order to be able to map from if you know which nodes you're at, then for example, you're here, and you want the things that okay, let's say you're at these things that end with A's, and you want to know where you can go with C. Well, then you do sort of a query, you do a range query, and then you go here. But in order to say, oh, well, if I'm between nodes 1 and 4, well, actually, there's an example on the next slide. So you need the out degrees, you need the in degrees, and you need the Burrows-Wheeler transform. Okay, so how you represent this, you represent the in and out degrees, you concatenate the unary representations. This is the standard way of doing it, standard in BOSS, for example. So this is 1, 1, 1, 1. You ignore the possibility of zeros for the moment. It just makes things complicated. This is 2. Okay, so here you have the 2, here you have the 2, and then you have the BWT, and then you have the C array, which is the frequency of the characters as labels. So this takes m bits, this takes m log sigma bits, which is going to be 2m for DNA, which is what we care about. Sigma log n bits, so ignore this, and another m bits. So suppose we want to leave node 9. Well, then, oh, n is the number of nodes, m is the number of edges. So just standard graph theory stuff. Sorry, no, I should have said that. So if you look at this, if we're at node 9 and we want to know where you go from node 9, well, then you're going to say, this is sort of simplified. I'm cutting some corners here. So you say, okay, well, where are the edges that go out of 9? And so this is going to be sort of B out, select 9. And that's going to sort of cutting some corners. That's going to tell you where you are. It's going to tell you where you look in the Boris-Wheeler transform. Then you're going to figure out this mapping, which is just the same as what you do in the BW in an FM index. So it's going to be the C array for A plus this rank, and this is 5, and this tells you where you go to the F array. So you know the interval in the F array, but that doesn't tell you which vertices you're at. So then you have to say, okay, well, you look at the in degrees and you say, okay, I'm at the 5th in edge. Which vertex is that arriving at? And so you do a rank query. Okay. And so you do all of this, and you see that node 9 goes to node 4. Node 4. Okay. So what's the problem? Well, for DNA, constant time navigation and standard compression of L, the BWT, B out and B in take about half the space. Okay. Just to represent the degree sequences. If we compress L better, there has been some work on that. Nicola Pratz's soda paper on some sneaky compression things. Then B out and B in could actually dominate. And the other problem is we're performing select queries on B out. And in these De Broglie graphs, you have lots of long stretches where it's in and out degree 1. So you tend to have a lot of 1s in B out. So you have runs of 1s. And so with standard implementations of bit vectors, those get flipped to 0s. And you're doing a select 0. And those queries are really slow and painful. So this is sort of a bottleneck. So how are we going to deal with this? Well, we're actually doing partial sum data queries on B out and B in. So you're doing a partial sum query on D out, the out degree sequence. Because you're saying, okay, well, from this node, I'm at this node, where does that section start in the BWT? So you're doing a sum query. And then when you go over to the ins, you're actually doing a search query. You're like, oh, well, I'm at this position, so I want something that sums to at most this. So you're doing a search query. So the question is, can we store D out and a D in compressed space? That's compressed in terms of those two sequences of numbers, not in terms of the B out and B in, which is the concatenation of the unary representations. Okay? And still support sum and search queries quickly. And the answer is yes, at least when the maximum degree is small. So actually, if you use some stuff from Diego and Rajiv, the answer was already yes. So this is a theorem. Let G be a Wheeler graph on n vertices with maximum degree delta. If delta and k, which is the order that you care about, are in little o of log n over log n squared, then we can store G's out degree sequence D out. In NHK, this is the degree, D out plus little o of n bits, such that it supports partial sum queries in constant time, and store G's in degree sequence D in NHK D in plus little o of n bits, such that it supports search queries in constant time. Okay, scariest slide of the talk, I hope. This is actually really easy. So it's one of those cases where you think, like, should this be a short Spire paper or a long homework? And I think the reviewer's comments convinced me that I should have made it a homework. Because they said, weak accept. The paper combines standard techniques to obtain a kth order compressed partial sum data structure that answers queries in constant time, provided that the answers are not too large. What I just said. The proofs are correct and the writing is good. However, the techniques are rather standard. And the result applies to a limited number of scenarios. Sequences of very small integers. Weak accept. The solution per here is pretty standard. So this is actually the proof sketch that I'm promising you. Represent the sequence S with a compressing scheme providing constant time random access to values of S. As S has only small values, the space of the representation can be bounded by NHKS plus little o n bits. Augment the above representation with sublinear data structures to support the two queries. It's very easy. If you really want to know, see the paper. But trust me, it's very standard. if you don't trust me, trust the reviewers. My main concern about is the goal of bounding the space usage in terms of the kth order entropy of S. Is there any reason for, say, H2 to be smaller than H1? So I'm not going to give you the proof. I'm going to try to address the questions that the reviewers had, because the proof is very standard. Okay. So for variance of de Broglie graph, sigma is delta is bounded by sigma, which is 4. So yes, I mean delta is going to be small. And it's standard to require that k be less than log base sigma n. And so this isn't actually, yeah, you could argue about it. It's not so much more restrictive. We're sort of used to this too. So why do you care about higher order empirical entropies? Because actually from the stuff by Diego and Rajiv, you already got the 0th order empirical entropy. And so what I'd like you to consider is this nasty looking little subgraph here. So suppose you have a directed edge labeled graph and it contains, this is a subgraph. This is not Wheeler. So your graph is not going to be Wheeler. So if anybody knows VG, so Yoni had this thing where basically you take a graph and try to make it Wheeler by embedding it in a high degree de Broglie graph. De Broglie graphs are everywhere. So what do you do? What do you get if you try to embed this in a high ordered? So suppose V is the only node reachable by TTGT, right? So you have TTGT and you get to V. And that's the only one here that's reachable by TTGT. And suppose it's the only one in the graph reachable by TTGT. Then everything over here where you can get to here by AAGC TTGT or CTCA TTGT. And those are all colex. If you list the vertices in this order 9 de Broglie graph, all of these vertices are going to be colexigraphically adjacent. And they're all going to have out degree equal to the out degree of V. So V is going to get copied lots and lots of times. Well, for TTGT, it's going to get copied 4 times because for this little subgraph, you've got 4 ways, AAGC, AACA, da, 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 da. So you're going to get 4 copies of 2 altogether in your out degree sequence. So this is actually going to give us this, I mean, this is sort of just hand wavy stuff. It leads to a conjecture. First conjecture, there are applications in which the out degree sequences, at least the out degree sequences, usually have long runs of 1s. That's actually something I got from the people who work on de Broglie graphs. And the other degrees cluster. Okay, so that clustering is something you don't always get with low degree, low k, small order empirical entropy. And the other conjecture is there are simpler and more practical approaches to storing compressed degree sequences. Okay, so I used stuff which is very standard and is actually used in practice, but I think there are easier ways to do this. So the last talk and we're over time, so I'm not going to drag it out unless people have questions. But I think I should have made this a homework. I didn't implement this. I think there are approaches which I sort of sketched in the paper which are implementable. And I think somebody should implement it. So hint, hint. Okay. Questions? I will turn this off before and we forget. Oh, maybe I need to go back and forwards. Oh, except there are no questions. Oh, okay.
Have you considered taking real Wheeler graphs and see the actual sequences of degrees and measuring the kth order entropy for 1, 2, and 3 and see what happens? I guess that's...
Yes, we considered that, and we ran into a sub-question, which is, what real Wheeler graphs? So it turns out the real Wheeler graphs are de Broglie graphs. So the only ones, yeah, I mean, what we should do is look at variable order De Broglie. So basically, Lin and Pevsner's manifold De Broglie graphs. They're not, so you can't do them with, for example, Jarno's trick that Simon presented at SIB. That only works for fixed K, at least as far as I understand. So this is saying, look, but it's easy to do this kind of thing for Wheeler graphs. And Wheeler graphs, you can do like the variable order K. And we actually, I think variable order K is more interesting and it's not hard to do. Look, the reviewers say this is trivial. So no, I mean, it's, but I think, yeah, we would have to get something that you can't do with that approach that from ESA that you can do with this, we'd have to do something like manifold De Broglie graphs. I did not actually do this.
Other questions? Okay, let's thank Travis again. And this is the end of the session. Thanks for your resistance.
Just some final comments. For tomorrow, please just send the slides for people that is presented in person, just to project it. And tomorrow will be raining, and we have the dinner. So please bring your coats. Shouldn't be that bad, the rain, but just in case, just be prepared. Okay. Thank you.